empty space weighs something. According to quantum field theory, every cubic centimetre of pure vacuum contains enough energy to power every star in the observable universe for trillions of years. This is called the Vacuum Catastrophe, and it's the most embarrassing failed prediction in the history of physics. We're wrong by 10 to the power of 120. That's not a rounding error. That's reality laughing at our equations. And yet this impossible, seething nothing is where everything came from. The universe didn't need a creator or a cause. It just needed quantum mechanics, false vacuum, and one spectacular accident during the first instant of time. Tonight, we're diving into the moment before existence, when the laws of physics were still being written, and something emerged from absolutely nothing. You're about to discover that nothing is the most terrifying concept in physics. Not the nothing of an empty room, or the silence of deep space. The quantum nothing. A void so unstable that it cannot help but create something. A vacuum so violent that it spawns universes. And the most disturbing part? This process is happening right now, everywhere around you, in every cubic centimetre of what you think is empty space. Let's start with a question that sounds simple, but leads to madness. What is nothing? Your instinct says nothing is the absence of everything. No matter, no energy, no light, no sound. Just pure emptiness, a blank slate, the ultimate zero. But quantum mechanics says you're wrong. Quantum mechanics says true nothingness cannot exist, and once you understand why, the entire universe starts to look different. Imagine you could remove everything from a region of space, every atom, every photon, every particle of matter or light. You create a perfect vacuum inside an invisible box. What's left inside? Classical physics, the physics of Newton and everyday experience says nothing is left. The box contains zero. But quantum physics tells a stranger story. Even in this perfect vacuum, something is happening. The void is seething. Heisenberg's uncertainty principle, one of the bedrock laws of quantum mechanics, says that certain pairs of properties cannot both be precisely known at the same time. You've probably heard this applied to position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it's moving. But the uncertainty principle also applies to energy and time, and this is where things get weird. The principle says that over very short time intervals, energy can fluctuate wildly. The vacuum can borrow energy, create particles from nothing, as long as those particles disappear quickly enough that the books balance. The shorter the time interval, the more energy can be borrowed. It's like the universe has a cosmic credit card with an infinite limit, as long as you pay it back before the statement closes. These aren't real particles in the traditional sense. They're called virtual particles. They pop into existence in matter-antimatter pairs, exist for a fleeting instant, then annihilate each other and vanish. An electron and a positron appear, dance for a trillionth of a second, then destroy each other. The energy borrowed from the vacuum is paid back. The universe's books balance. And all of this happens in what looks like perfectly empty space. You might think this is just theoretical speculation, mathematical abstraction, with no connection to reality. But virtual particles create measurable effects. One of the most famous is the Casimir effect. Take two perfectly flat metal plates and place them extremely close together in a vacuum, just a few nanometers apart. Classical physics says nothing should happen. There's no matter between the plates, no forces acting, just empty space. But if you measure carefully, you'll find the plates are being pushed together by a tiny but very real force. Here's why. Virtual particles of all wavelengths can exist in the vacuum outside the plates, but between the plates, only virtual particles with wavelengths small enough to fit in the gap can exist. This creates an imbalance. There's more vacuum pressure outside the plates than between them. The plates are squeezed together by the quantum vacuum itself, by nothing. This effect has been measured in laboratories with extraordinary precision. The force is tiny, but it's there. You can feel the pressure of nothing. Empty space has texture, structure, weight. The vacuum is not a passive void. It's an active participant in physical reality. But the Casimir effect is just the beginning. When physicists try to calculate how much energy the quantum vacuum should contain, they get an answer so absurdly large that it threatens to destroy our entire understanding of the cosmos. This is the vacuum catastrophe I mentioned at the start, and it's not a small problem. Quantum field theory, our best description of how particles and forces work, says that every point in space should contain contributions from all possible virtual particles: electrons and positrons, quarks and antiquarks, photons, neutrinos, everything the quantum vacuum can briefly create. When you add up all these contributions, the energy density of empty space should be enormous. Calculations suggest the vacuum energy should be about 10 to the power of 120 times larger than what we actually observe. Let me put that number in perspective. If I write out 10 to the power of 120, that's a 1 followed by 120 zeros. That's not just wrong, that's spectacularly, catastrophically, embarrassingly wrong. It's like predicting someone's height will be 120 orders of magnitude taller than they actually are. You'd be predicting they're larger than the observable universe when they're actually 5 feet tall. This is often called the worst prediction in the history of physics, and yet, despite being wrong by this incomprehensible margin, quantum field theory works perfectly in every other way. It predicts the behaviour of particles with stunning accuracy. The magnetic moment of the electron, for example, has been calculated and measured to agree to within 1 part in a trillion. Quantum mechanics is the most precisely tested theory in all of science. Except when it comes to the vacuum. There, it fails so dramatically that something must be fundamentally wrong with our understanding. So what's actually happening? Either quantum mechanics is missing something crucial about how vacuum energy works, or there's some unknown mechanism that cancels out most of the vacuum energy, leaving just a tiny residue. That tiny residue is what we call dark energy, the mysterious force that's causing the universe to expand faster and faster. Dark energy makes up about 68% of all the energy in the universe, and we have no idea what it is. Some physicists think dark energy might be vacuum energy, but with most of it somehow suppressed or cancelled. Others think it's a completely different kind of field-pervading space. Still others propose that we need to modify Einstein's equations, that gravity works differently on cosmic scales than we think. The truth is, we're as ignorant about dark energy as ancient humans were about lightning. We can observe it, measure it, but we don't understand it. But here's what we do know. The vacuum is not nothing. It has energy. It has pressure. It affects how particles behave. And most importantly for our story tonight, this unstable, energetic quantum vacuum is where the entire universe came from. Everything you see around you, every star, every galaxy, every atom in your body, emerged from a vacuum fluctuation 13.8 billion years ago. The universe is the ultimate something from nothing. Now you might be thinking, hold on, if virtual particles have to pay back their borrowed energy and disappear almost instantly, how did the universe borrow energy and never pay it back? How did virtual particles become real? This is where we need to talk about what happened during the first incomprehensibly brief moment after the Big Bang, or more precisely, what happened before the Big Bang as we usually think of it. The moment we're going to explore is so short that human language breaks down trying to describe it. We're talking about the Planck time, 10 to the power of negative 43 seconds. That's a decimal point followed by 42 zeros and then a 1. If a single second were stretched to the age of the universe, the Planck time would be about 1/10 of a second in comparison. At this scale, space and time themselves become grainy, quantum, uncertain. At the Planck scale, space is not a smooth fabric, but a roiling foam of quantum fluctuations. Tiny wormholes and black holes pop into existence and evaporate. The geometry of space-time itself fluctuates wildly. Distance and duration lose their meaning. This is quantum foam, and it represents the absolute limit of how finely we can probe the structure of reality. Below the Planck scale, our current theories simply stop working. The equations blow up. Infinity appears where it shouldn't. We're at the edge of known physics. But even though we can't describe what happens below the Planck scale, we can describe what happened just above it. And what happened was the most violent event in cosmic history. In less time than it takes light to cross the width of a proton, the universe expanded by a factor of at least 10 to the power of 26. Space itself inflated faster than the speed of light. This period is called cosmic inflation, and it's the reason the universe exists in its current form. Before we dive into inflation, let me address the obvious question. How can anything expand faster than light? Doesn't Einstein's relativity say nothing can move faster than light? It does. But here's the loophole. Nothing can move through space faster than light. But space itself has no speed limit. Space can expand as fast as it wants. During inflation, points in space were separating faster than light could travel between them. Not because anything was moving, but because new space was being created between them at an incredible rate. Imagine you're an ant on a balloon. You can only walk so fast across the balloon surface. That's like the speed of light, your maximum speed through space. But now imagine the balloon is being inflated so rapidly that even though you're walking forward, the ant you're trying to reach is moving away from you faster than you can walk. The balloon's expansion, the creation of new surface, is outpacing your maximum speed. That's what happened during cosmic inflation. But what drove this insane expansion? The answer involves something called the inflaton field. Now, fields are everywhere in physics. The electromagnetic field carries the electromagnetic force. The Higgs field gives particles mass. Quantum field theory says that every type of particle is actually a ripple or excitation in its corresponding field. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. The inflaton field is hypothetical. We haven't detected it directly, but the evidence for its effects is overwhelming. This field, if it exists, has a very unusual property. Most fields are stable when they are at their minimum energy state, like a ball resting at the bottom of a valley. But the inflaton field got stuck in what's called a false vacuum state. It was sitting on a higher energy level, like a ball balanced on a shelf, not yet having rolled down to the valley floor below. While the inflaton field was stuck in this false vacuum, it created a form of energy that had a bizarre property. Instead of gravity pulling things together, this vacuum energy created repulsive gravity. It pushed space apart. And because this energy was a property of the vacuum itself, as space expanded, more space meant more vacuum energy. More vacuum energy meant faster expansion. More expansion meant even more vacuum energy. It was a runaway feedback loop. During this brief moment of inflation, the universe doubled in size, then doubled again, then doubled again. And this happened dozens of times in an interval so short you couldn't blink. The numbers are difficult to comprehend. In about 10 to the power of negative 35 seconds, a region of space smaller than a proton expanded to roughly the size of a basketball. Then it kept going. By the time inflation ended, that tiny patch had grown larger than the observable universe today. Think about that for a moment. Everything you can see with the most powerful telescopes, all the galaxies spanning billions of light years, once fit inside a volume smaller than an atom. And it expanded to cosmic scales in less time than it takes light to cross the width of a proton. This is the most rapid change in the history of the universe. Nothing before or since has even come close. But here's the part that connects back to our quantum vacuum. During inflation, quantum fluctuations in the inflaton field were stretched from subatomic scales to cosmic scales. Remember those virtual particles popping in and out of existence in the quantum foam? During inflation, some of those fluctuations got stretched so fast that they didn't have time to disappear. They became real, permanent variations in the energy density of space. These tiny quantum fluctuations, these ghosts from the seething vacuum, became the seeds of everything. Regions that were slightly denser than average had a bit more gravity. They pulled in more matter. Over millions and billions of years, these tiny density variations grew into the galaxies, stars, and planets we see today. You exist because of quantum fluctuations amplified by cosmic inflation. Your body is made of atoms forged in stars that formed in galaxies that grew from density ripples that started as virtual particles in the quantum vacuum. The cosmic microwave background radiation, that ancient light left over from when the universe first became transparent, still carries the imprint of these primordial quantum fluctuations. Satellites like WMAP and Planck have mapped the temperature variations in this radiation with exquisite precision, and the pattern matches exactly what inflation theory predicts. We can see the fingerprints of quantum mechanics written across the entire sky. But inflation creates a deeply unsettling possibility. If inflation happened once, it might happen again. In fact, the same quantum fluctuations that seeded galaxies might also seed new regions of inflation. Right now, somewhere in the vastness of space, a quantum fluctuation might be triggering a new episode of inflation, a bubble of rapidly expanding space growing at the speed of light. And if that bubble ever reached us, everything would be destroyed in an instant. Inside an inflating bubble, the laws of physics might be completely different. The constants of nature, things like the strength of gravity or the charge of an electron, might have different values. Our atoms would disintegrate. The forces holding matter together would change. We wouldn't even see it coming. One moment you'd be reading these words, the next, you'd be erased as a wall of altered physics swept past at light speed. But even more disturbing than the possibility of future inflation is what inflation implies about the universe we live in. If inflation can happen anywhere due to quantum fluctuations, and if inflation creates vast regions of space, then our observable universe might be just one bubble in an infinite sea of bubbles. Each bubble could have different physics, different constants, different laws. This is the multiverse hypothesis, and it emerges naturally from inflation theory combined with quantum mechanics. Some physicists hate the multiverse idea. It seems unfalsifiable, more philosophy than science. If we can never observe these other universes, how can we test whether they exist? But other physicists point out that inflation plus quantum mechanics almost demands a multiverse. If you accept that inflation happened here, and you accept quantum mechanics, then quantum fluctuations should be triggering inflation constantly throughout a larger space we'll never see. This means that while you're listening to these words, trillions of universes might be inflating into existence. Each one a cosmos as vast as ours, with its own galaxies, its own stars, its own laws of physics. And we'll never know about any of them because they're expanding away from us faster than light can travel. They're beyond our cosmic horizon forever. But let's return to the question that started all of this. What happened before the Big Bang? What existed 1 second before time began? These questions reveal a deep confusion about the nature of time itself. You're thinking of time as a river, flowing from past to future, and the Big Bang as an event within that river. But that's not how it works. Time is not something the universe exists within. Time is a property of the universe. It's part of the fabric of space-time. Einstein's relativity merged space and time into a single four-dimensional structure. You can't have time without space. You can't have space without time. They're woven together into space-time, and space-time itself was created during the Big Bang, or more accurately, during inflation. So asking what happened before the Big Bang is like asking what's north of the North Pole. The question contains a category error. There is no north of the North Pole because north is defined by the geometry of Earth's surface, and at the pole, that direction ceases to exist. Similarly, there is no before the Big Bang because time itself began with the expansion of space. The word before requires time, and time didn't exist yet. Stephen Hawking liked to use this North Pole analogy. he'd point out that just as you can't go further north than the North Pole, you can't go further back in time than the Big Bang. Time has a boundary. It's not infinite in the past, it had a beginning. This doesn't mean something caused time to start. Causation requires time. You have a cause that comes before an effect. But if time itself is beginning, there's no before for a cause to exist in. This is profoundly strange. Your intuition demands that everything has a cause, that nothing can come from nothing, that there must be something before. But your intuition evolved to deal with falling objects and thrown spears, not the origin of space-time itself. At the fundamental level, the universe doesn't obey your intuitions. It obeys quantum mechanics and relativity, and those theories paint a picture that's far stranger than common sense allows. But some physicists push back against this. They point out that quantum mechanics itself might allow for something before the Big Bang, or at least something that plays the role of before even if time doesn't exist yet. One idea involves quantum tunneling, that weird phenomenon where particles can pass through barriers they shouldn't be able to cross. In quantum mechanics, a particle trapped in a potential well can tunnel through the well's walls and escape, even if it doesn't have enough energy to climb over the walls classically. This happens because of the wave nature of quantum mechanics. The particle's wave function extends slightly beyond the barrier, giving it a small probability of appearing on the other side, and what has a probability in quantum mechanics will eventually happen if you wait long enough. Alexander Vilenkin and others have proposed that the universe itself quantum tunneled into existence from nothing. Before the universe, there was not a void or empty space, but a state of no space, no time, pure geometric nothing. But this nothing was governed by the rules of quantum mechanics, and quantum mechanics says that such a state is unstable. It will fluctuate, and one of those fluctuations could tunnel into a state where space and time exist. In this picture, the universe didn't need a cause, it just needed quantum mechanics and probability. Given infinite opportunities in timeless nothing, eventually a fluctuation would occur that created space-time. Our universe would be the result of quantum tunneling from nothing into something. It's a universe that literally pulled itself up by its own bootstraps. Another approach comes from loop quantum gravity, a theory that tries to merge quantum mechanics with Einstein's general relativity. In this framework, space itself is not continuous but made of discrete units. Quantum grains of space link together like atoms in a crystal. Time also becomes grainy at the Planck scale. When you apply loop quantum gravity to the early universe, something remarkable happens. The singularity predicted by classical relativity, that point of infinite density and infinite curvature at the Big Bang, disappears. It's replaced by a quantum bounce. The universe contracts to an incredibly small size, but before it reaches zero, quantum effects create a repulsive force that causes it to bounce back and expand. The Big Bang becomes the Big Bounce. In this scenario, our universe might have been preceded by a previous universe that collapsed. At the moment of maximum contraction, when densities reached the Planck scale, quantum gravity kicked in and reversed the collapse into an expansion. Time didn't begin at the Big Bang. It continued through from the previous cycle. The bounce might have erased most information about what came before, but it wasn't a true beginning. It was a transition. These ideas, quantum tunneling from nothing and the big bounce, are speculative. We don't have a complete theory of quantum gravity yet. We can't probe the Planck scale directly with experiments, but these approaches show that even the question of what came before might have answers that don't require anything supernatural or outside physics. The universe might be self-creating, self-causing, a loop of existence that needs nothing beyond itself to explain why it's here. But regardless of whether there was something before or whether time itself began with the Big Bang, we can still ask why the universe has the properties it does. Why these laws of physics? Why these constants of nature? Why is the universe so precisely tuned for the existence of complexity and life? This is called the fine-tuning problem, and it's one of the deepest puzzles in cosmology. The universe appears to be balanced on a knife edge. If gravity were slightly stronger, Stars would burn out in millions of years instead of billions, not giving planets time to form or life to evolve. If the electromagnetic force was slightly different, atoms wouldn't be stable. If the mass of the electron were a bit larger, chemistry as we know it couldn't exist. Change any of dozens of physical constants by tiny amounts, and the universe becomes sterile. No stars, no planets, no chemistry, no life. The margins are astonishingly narrow. Some of these constants appear fine-tuned to 1 part in 10 to the power of 60 or more. It's as if someone dialed in the settings with extraordinary precision to create a universe where complexity could emerge. This fine-tuning makes some people argue for a designer, an intelligence that set the cosmic dials just right. But there's another explanation that emerges naturally from everything we've discussed: the multiverse. If inflation creates countless bubble universes, each with randomly varying physical constants, then most of those universes would be sterile, dead, unable to support any kind of complexity or life. But in a tiny fraction of those universes, just by chance, the constants would land in the narrow range where stars can form, chemistry can happen, and life can evolve. And here's the key insight. We can only exist in one of those rare, finely tuned universes. We can't observe the vast number of sterile universes because there's no one there to observe them. This is called the anthropic principle. The universe looks fine-tuned for life because if it weren't, we wouldn't be here to notice. It's like a puddle waking up one morning and thinking how amazing it is that the hole in the ground fits it so perfectly. Of course the hole fits. If it didn't, the puddle would be somewhere else. Similarly, of course, our universe has the right properties for life. If it didn't, we'd be in one of the countless other universes that does, or we wouldn't exist at all. The anthropic principle bothers a lot of physicists. It feels like giving up on finding a deeper explanation. But if the multiverse is real, if inflation plus quantum mechanics really does create an infinite variety of universes, then the anthropic principle might be the only explanation available. The constants of nature in our universe are what they are because we're in one of the rare patches where life is possible. It's selection bias on a cosmic scale. But even if you accept the multiverse and the anthropic principle, there are still deeper questions. Why do the laws of physics take the form they do? Why is there quantum mechanics at all? Why is there something rather than nothing? These questions might not have answers, or rather, the answer might be that there is no why. The laws of physics might be brute facts, unexplainable foundations upon which everything else rests. This is where physics meets philosophy, and it's where many scientists become uncomfortable. Science is about finding explanations, building models, making predictions. But when you push back to the very foundations of reality, you eventually hit bedrock. You find facts that just are, with no deeper explanation available. The laws of physics might be that bedrock, or maybe not. Maybe there's an even deeper theory waiting to be discovered. A theory that explains why quantum mechanics has the form it does, why space-time exists, why anything exists at all. String theory attempts to be that deeper theory. It proposes that the fundamental constituents of reality are not particles but tiny vibrating strings. Different vibration modes correspond to different particles. The laws of physics emerge from the mathematics of these strings vibrating in a 10 or 11-dimensional space-time. String theory is mathematically beautiful and surprisingly constraining. You can't just make up any laws you want. The mathematics forces certain structures to exist. In that sense, string theory hints at the possibility that the laws of physics might be inevitable consequences of mathematical consistency. Maybe the universe is the way it is because it's the only way it could be. But string theory remains unproven. We don't have experimental evidence for strings. We might never have such evidence. The energy scales where string effects become important are far beyond anything we can produce in particle accelerators. String theory might be untestable, and, if it's untestable, is it even science? These questions about the foundations of reality take us to the limits of human knowledge. we've traced the universe back to the first fraction of a second, to quantum foam and inflation and vacuum energy. We've explored how something emerged from nothing through quantum mechanics. But there's a sense in which we're not much closer to understanding existence itself than our ancestors who wondered at the stars. You might feel frustrated by this. You came here looking for answers about how the universe began, and instead you found more questions, deeper mysteries and theories that might be forever untestable. But there's something beautiful in this, something profound in reaching the limits of explanation and standing at the edge of the unknown. The universe doesn't owe us an explanation. It doesn't owe us comprehensibility. The fact that we've come as far as we have, that we've traced reality back to quantum foam and Planck times and cosmic inflation, is remarkable. We've learned to speak the universe's mathematical language well enough to predict how particles behave, how stars form, how galaxies evolve. We've looked back 13.8 billion years and seen the echo of creation in the cosmic microwave background, and we've discovered that the foundation of everything is quantum uncertainty. The vacuum that seems empty is full of potential. Nothing is unstable. It fluctuates. It borrows energy from somewhere or nowhere, and occasionally those fluctuations grow into universes. Our universe, with its hundreds of billions of galaxies and trillions of stars and unfathomable reaches of space, started as a quantum fluctuation in a vacuum that might itself have emerged from truly nothing at all. You're made of atoms forged in stars that formed from gas clouds seeded by quantum fluctuations amplified by inflation. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it traces back through an unbroken chain of cause and effect to those first moments when space inflated and virtual particles became real. You are the universe examining itself. You are quantum foam that learned to think. There's a tendency to feel small and insignificant when confronted with cosmic scales. The universe is vast and old and filled with more stars than you could count in 1,000 lifetimes. What's one human life against that immensity? But this perspective misses something crucial. The complexity in your brain, the thoughts you're having right now, the consciousness that's aware of reading these words is the most complex structure we know of in the universe. Stars are simple. Hydrogen fuses into helium, gravity and gas pressure balance. The physics is well understood. Galaxies are collections of stars, gas and dark matter following predictable orbital mechanics. Even black holes, for all their strangeness, obey relatively simple equations. But your brain, with its 86 billion neurons and trillions of synaptic connections, creates consciousness through processes we barely understand. You're more complex than a star, more mysterious than a galaxy. And here's the remarkable thing. The same quantum mechanics that describes virtual particles and vacuum energy also describes the electrons in your neurons. The same uncertainty principle that allows energy to fluctuate in empty space also governs the behavior of atoms in your DNA. The same laws of physics that created the universe also create your thoughts. There's no separate realm of biology or mind. It's all physics. It's all quantum fields and forces and particles following the same rules from the Planck scale to the cosmic scale. This unity is part of what makes physics so powerful and so beautiful. Every atom obeys the same laws. The rules that govern fusion in the core of distant stars are the same rules that govern chemistry in your cells. When we look at the universe, we're not seeing something separate from ourselves. We're seeing the same stuff we're made of, arranged differently, existing at different scales and times. Now, about 2 hours into this journey, let me shift the tone slightly. We've covered a lot of intense physics, a lot of mathematical strangeness and cosmic violence. If your mind feels stretched, if the concepts are starting to blur together, that's completely natural. We're dealing with ideas that took physicists decades to develop and accept. You're not expected to grasp every detail on first hearing. Let the concepts wash over you. Let your mind rest on the parts that resonate. The next parts of our journey will move through some of the same territory, but with a gentler touch. We're going to explore what these abstract concepts mean, not just mathematically, but experientially. What does it feel like to really sit with the idea that nothing is unstable? What changes in how you see the world around you when you know it's all quantum fluctuations grown large? Think about the space around you right now. Whether you're lying in bed or sitting in a chair or walking under open sky, the air around you seems empty in the gaps between molecules. But now you know it's not empty. It's seething with virtual particles, electron-positron pairs blinking in and out of existence, photons flickering through the quantum foam. The vacuum is alive with invisible activity. Every cubic centimetre of space, every cubic millimetre, every volume down to the Planck scale is filled with this quantum dance, and all of it, every virtual particle, every fluctuation, is governed by the same uncertainty principle that made the universe possible. The space between your fingers as you hold this device or touch this page contains the same physics that created galaxies. This isn't metaphor or poetry, it's literal. The quantum vacuum around you is the same quantum vacuum that existed before the Big Bang. The fields that fill your room are the same fields that filled the primordial universe. Time has passed, space has expanded, but the fundamental substrate hasn't changed. You're sitting in the same quantum foam that inflated into the cosmos. And here's a thought that might help the scale feel less alien. Your body replaces most of its atoms every few years. The calcium in your bones, the phosphorus in your DNA, the oxygen in your tissues, all of it cycles through. You're constantly exchanging matter with your environment. The atoms that make you up today will be scattered across the world in a decade. But those atoms aren't you. You are the pattern, the information, the arrangement of matter that maintains itself despite constant flux. And patterns like you emerge naturally from the laws of physics given enough time and the right conditions. The universe doesn't just permit complexity. Under the right circumstances, it demands it. After the Big Bang, after inflation ended, and the universe began expanding more sedately, it was filled with hot, dense plasma. Protons and electrons were moving too fast to form stable atoms. The universe was opaque, a fog of charged particles scattering light in every direction. But as space expanded, it cooled. And about 380,000 years after the Big Bang, the temperature dropped enough for electrons to combine with protons and form neutral hydrogen. This moment, called recombination, was when the universe first became transparent. Light could suddenly travel freely through space. The photons released at that moment have been travelling ever since, stretched by cosmic expansion into microwaves. That's the cosmic microwave background, the oldest light in the universe, and it shows us the universe as it was when it first became clear. But even though atoms had formed, there were no stars yet, no galaxies, just a nearly uniform fog of hydrogen and helium filling all of space. The universe entered what's called the cosmic dark ages. There were no light sources, no fusion reactions, just darkness and cold gas gradually clumping under its own gravity. Those clumps grew slowly at first, dense regions pulling in nearby gas. Remember, these density variations started as quantum fluctuations during inflation. Tiny ripples in the inflaton field became tiny differences in matter density. And over millions of years, gravity amplified these differences. Denser regions became denser. They pulled harder on their surroundings. They grew. Eventually, some of these clumps became dense enough and hot enough for fusion to ignite. The first stars formed. This moment, perhaps 100 million years after the Big Bang, is called the cosmic dawn. The universe lit up for the first time since recombination. And with starlight came something new, heavy elements. The Big Bang created only the lightest elements, hydrogen, helium, and traces of lithium and beryllium. That's it. No carbon, no oxygen, no iron. Nothing that chemistry could build complex molecules from. But inside the cores of stars, fusion builds heavier elements. Hydrogen fuses to helium, helium to carbon and oxygen, carbon to neon, magnesium, silicon, and in the most massive stars, all the way up to iron. When these massive stars exhaust their fuel, they explode as supernovas. The explosion creates even heavier elements and scatters them into space. Later generations of stars form from gas clouds enriched with these heavy elements. Planets form from the same enriched material, and on at least one planet orbiting an ordinary star in an unremarkable galaxy, some of those heavy elements arrange themselves into self-replicating molecules. Life began. This process took billions of years. Stars had to form, live, die, and scatter their ashes. New stars had to form from those ashes. Planets had to coalesce. Oceans had to fill with water. Continents had to form. And only then, only after all that preparation, could chemistry become complicated enough for life. You are made of stardust. That's not poetic exaggeration. The atoms in your body, except for the hydrogen, were forged inside stars that exploded before the sun existed. The oxygen you breathe was made by massive stars that died in supernovas billions of years ago. The calcium in your bones was synthesized in stellar cores. The iron in your blood came from supernovas or colliding neutron stars. Every breath you take connects you to the death of stars. Every heartbeat moves atoms that once burned in nuclear furnaces hotter than anything on Earth. You are the universe rearranged into a pattern complex enough to wonder about its own origins. And now, having wondered, having traced the chain of causation back through stars and galaxies and inflation to quantum foam, you understand something profound. There's no separation between you and the cosmos. You're not a tiny isolated thing separate from the vastness out there. You're a part of it. A temporary eddy in the flow of matter and energy. A pattern that emerged naturally from the same laws that govern everything else. The quantum fields that create virtual particles also create the particles in your body. The uncertainty principle that lets the vacuum fluctuate also governs the chemistry in your cells. This realization can be overwhelming. But it can also be deeply comforting. You're not separate. You're not alone. You're woven into the fabric of existence as thoroughly as anything can be. When you look at the stars, you're not seeing something other. You're seeing your own origins. You're seeing where the atoms in your body were forged. You're looking at family. Now we're about 3 hours into this journey together, and I want to shift into an even gentler space. The concepts we've explored, quantum mechanics and inflation and vacuum energy, these are intellectually demanding. They challenge intuition. They require holding multiple strange ideas in mind simultaneously. And if you've made it this far, whether you're still awake or drifting in that pleasant space between consciousness and sleep, you've done remarkable work. What we're going to do now is let these ideas settle. We're going to revisit some of the themes, but without the same intensity. Think of this as a long, slow integration of everything we've discussed, a chance to sit with the strangeness and let it become familiar. Let's return to the vacuum, that quantum foam that fills all of space. But this time, instead of focusing on the mathematics or the catastrophe of wrong predictions, let's focus on what it means. The vacuum is potential, it's possibility. It's the field of all fields, the ground state from which everything emerges and to which everything returns. When a virtual particle pair appears in the vacuum, exists briefly, then annihilates, where does it go? It returns to potential. The energy borrowed is paid back. The books balance. But during that brief existence, the particles were real. They affected their surroundings. They contributed to forces and fields. Their existence mattered, even though it was temporary. You could think of yourself the same way. You're a pattern that emerged from the quantum substrate, persists for a while, then dissolves back into the flow. The atoms that make you up came from stars and will return to space. The energy that powers your thoughts comes from food, which got it from sunlight, which came from fusion in the sun's core. You're a temporary concentration of energy and information, borrowed from the universe and eventually to be returned. This might sound bleak, but there's another way to see it. Your temporary existence is no less real than the eternal existence of protons. In fact, the proton isn't even truly eternal. Given enough time, perhaps 10 to the power of 34 years or more, protons might decay into lighter particles. Even the most stable matter is temporary on long enough timescales. Everything is temporary. Every star will burn out. Every galaxy will exhaust its gas and stop forming stars. Every black hole will eventually evaporate through Hawking radiation. On timescales so vast they dwarf the current age of the universe, everything dissolves. The universe approaches a state of maximum entropy, a cold, dark, empty expanse where nothing changes anymore because there's no energy left to drive change. This is called the heat death of the universe, and it's the most likely fate of the cosmos if dark energy continues behaving as it does now. Expansion will accelerate. Galaxies will drift beyond each other's horizons. Stars will fade. Black holes will evaporate. And after an incomprehensible amount of time, the universe will be cold, dark, and empty. Nothing but a thin haze of radiation stretched across infinite space. But even this far future connects back to our beginning. The vacuum energy driving cosmic expansion might eventually decay. Some theories suggest that the false vacuum we're in now might not be perfectly stable. Given enough time, a quantum fluctuation could trigger a decay to a true vacuum state with lower energy. This decay would create a bubble expanding at the speed of light, destroying everything in its path. Inside the bubble, physics would be different. The vacuum energy would be lower, perhaps zero. Space might stop expanding or even contract. All the structures we know, atoms, nuclei, possibly even protons, might become unstable. The universe inside the bubble would be fundamentally different from ours. And here's the unsettling part. This could happen at any moment. Quantum mechanics is probabilistic. There's a tiny but non-zero chance that a vacuum decay is occurring somewhere right now. We wouldn't know until the bubble wall reached us, and then we'd be erased instantly. Everything you know, everything that exists wiped out by a wall of altered physics moving at light speed. The probability is incredibly small. Physicists have calculated that such an event is extraordinarily unlikely over timescales much longer than the current age of the universe. But unlikely isn't impossible, it's just very, very improbable. The vacuum we're in appears stable enough that we don't need to worry. But it's a reminder that existence itself is contingent, balanced on quantum probabilities. This might make existence feel fragile, precarious, like we're all dancing on the edge of a cliff. But there's another perspective. Every moment you exist is a moment the universe hasn't decayed. Every breath is a probabilistic victory. The fact that you're here, now, aware and thinking, means that in this region of space-time, in this bubble of reality, the vacuum has held stable for 13.8 billion years. And during that time, the universe has created stars, planets, life and minds capable of understanding their own origins. That's extraordinary. Against the backdrop of infinite nothing, against the default state of non-existence, the universe has bootstrapped itself into incredible complexity. And you're part of that complexity. You're one of the ways the universe understands itself. Carl Sagan famously said, "We are a way for the cosmos to know itself." And this is literally true. The atoms in your brain, arranged just right, create consciousness. Those atoms came from stars. Those stars came from gas clouds seeded by quantum fluctuations. Those fluctuations came from the vacuum. The vacuum came from, well, we're not sure. Maybe nothing. Maybe quantum tunneling from a state of no space and no time. Maybe a previous universe that bounced. But regardless of the ultimate origin, here you are. Consciousness. Awareness. The universe looking at itself and wondering how it got here. Your existence is improbable, contingent on billions of years of cosmic evolution, and countless chance events, but you're here. And while you're here, you're part of the story. You're part of how the universe unfolds. Now let your thoughts drift. Let the concepts we've explored settle into the background. Quantum mechanics, inflation, virtual particles, vacuum energy, dark energy. The Big Bang, the cosmic microwave background, fine-tuning, the multiverse. All of these ideas are lenses for understanding reality, but reality itself is right here, right now, in your immediate experience. The breath moving in and out of your lungs, the sensation of weight where your body contacts the surface beneath you, the quiet sounds around you, near or far, the darkness behind your closed eyelids or the dim light if they're open. This immediate experience is just as fundamental as the quantum fields underlying it. Maybe more so, because this is the only way you actually encounter the universe. Physicists study the universe by breaking it down into components, by finding patterns, by building mathematical models. And this approach has been incredibly successful. We've learned astonishing things about how reality works. But the model is not the territory. The equations that describe quantum mechanics are not the same as the experience of existing as a quantum system. You don't experience your electrons as probability waves. You don't feel virtual particles in the vacuum around you. You don't perceive the quantum foam seething at the Planck scale. You experience solidity, continuity, causation, and that experience is valid. It's not an illusion. It's what quantum reality looks like at your scale, filtered through your senses and your nervous system. So while it's useful to know that matter is mostly empty space, that atoms are clouds of probability, that forces are mediated by virtual particles, you don't need to hold all that in awareness constantly. You can let it be background knowledge. You can trust that the universe follows its laws without needing to consciously track every detail. Let yourself relax more deeply now. Let your attention soften. The universe is vast and strange and filled with mysteries we may never solve. But you're part of it. You belong here. The quantum fields that permeate space also permeate you. The forces that hold atoms together hold you together. The same laws govern everything. And those laws, strange as they are, have created conditions where complexity can emerge, where molecules can replicate, where evolution can sculpt organisms capable of thought and feeling, where consciousness can arise and look back at the universe that created it with wonder and curiosity. You are that wonder, that curiosity, that looking back. And whether you're awake or asleep, conscious or dreaming, you're always part of the cosmos. There's nowhere else you could be, nothing else you could be made of. You're a pattern in the quantum foam, a thought the universe is having, a wave in the field of existence. Rest in that knowledge. Let it support you. The universe doesn't require your understanding to continue existing. It doesn't need your attention to follow its laws. You can let go. You can stop trying to hold all the pieces together. The quantum fields will keep fluctuating. Virtual particles will keep appearing and disappearing. Space will keep expanding. Stars will keep fusing hydrogen. And you can simply be, right here, right now, part of it all, temporary but real, improbable but present, a moment of consciousness in the vast unfolding of existence. As we approach the end of our journey, let me bring things to a close with a few final thoughts. We started with the Vacuum Catastrophe, that spectacular failure of prediction, where quantum field theory gets the energy of empty space wrong by 120 orders of magnitude. We explored how the quantum vacuum is not nothing but a seething foam of virtual particles. We traced the universe back to cosmic inflation, that moment of impossible expansion when a tiny patch of space smaller than a proton grew to cosmic scales in an instant. We saw how quantum fluctuations were stretched during inflation and became the seeds of galaxies. We discussed how time itself might have begun with the Big Bang, how the question, what came before, might be meaningless. We explored possible answers to that question anyway. Quantum tunneling from nothing, the big bounce from a previous universe, The multiverse where countless bubble universes inflate with different physics. And we discussed fine-tuning, the observation that our universe seems precisely calibrated for complexity and life. Through it all, we've seen how quantum mechanics sits at the foundation of everything. The uncertainty principle that lets the vacuum fluctuate also lets the universe emerge from nothing. The probabilistic nature of quantum events means existence itself is contingent, a matter of chance rather than necessity. And yet here we are, the universe looking back at itself, made possible by that quantum uncertainty. What does this mean for you? Maybe nothing. Maybe everything. Maybe it changes how you see the world around you, knowing that empty space is full of invisible activity. Maybe it shifts something in how you think about your place in the cosmos, understanding that you're made of the same stuff as stars, governed by the same laws, part of the same unfolding story. Or maybe it's just interesting information, concepts to think about when you have time, then set aside when daily life demands your attention. And that's fine too. The universe doesn't demand anything from you. It doesn't require your understanding or your reverence. It simply is, and you simply are. And for this moment, those two facts coincide. Thank you for staying with me through this long exploration. Whether you're still awake or long since asleep, whether these ideas have settled into understanding or remain comfortingly mysterious, I'm glad you took this journey. The universe began from nothing, or from quantum foam, or from a previous universe bouncing back. It inflated impossibly fast. It cooled and formed atoms, stars ignited, galaxies assembled, planets formed. And on at least one planet life emerged. And that life eventually produced you, a mind capable of wondering about its origins, capable of tracing the chain of causation back to quantum foam and virtual particles and vacuum energy, capable of asking questions that push at the boundaries of physics and philosophy. Questions like, why is there something rather than nothing? Questions that might not have answers but are worth asking anyway. Rest now. Let these thoughts drift into dreams or dissolve into sleep. The universe will keep expanding. The quantum vacuum will keep fluctuating. Stars will keep burning. And you will keep being, for now, part of this impossible, improbable, beautiful existence. From nothing to something. From quantum foam to consciousness. From the beginning that wasn't quite a beginning to this moment here now with you. The universe began from quantum fluctuations, borrowed energy that became real through inflation, and created everything from nothing. But what happened next is equally remarkable. After inflation ended, after that violent expansion slowed to a more sedate pace, the universe entered a new phase. It was no longer inflating exponentially, but it was still expanding, still cooling, still evolving. When inflation ended, the energy stored in the inflaton field had to go somewhere. Remember, this field had been stuck in a false vacuum state, a high-energy configuration that drove exponential expansion. When the field finally rolled down to its true minimum energy state, all that stored energy was released. It didn't just disappear. Energy can't be created or destroyed. It transformed. This transformation is called reheating. The inflaton field decayed into a hot bath of particles and radiation. All the energy that had been locked up in the vacuum state converted into matter and antimatter, particles, photons, everything the quantum fields could produce. The universe went from cold and empty during inflation to incredibly hot and dense immediately after. The temperature during reheating might have been as high as 10 to the power of 27 degrees Kelvin. That's a trillion times hotter than the core of the Sun. At these temperatures, particles we never see in ordinary matter were common. Quarks and gluons existed freely, not bound into protons and neutrons. W and Z bosons, the particles that carry the weak nuclear force, were being created and destroyed constantly. Even the Higgs boson, that particle we only discovered in 2012 after building the Large Hadron Collider, would have been abundant. This was a true particle soup, Everything mixed together. Matter and antimatter in equal amounts, constantly being created from energy and annihilating back into energy. The universe was an enormous particle accelerator, far more energetic than anything we could ever build on Earth. And in this chaos, the fundamental forces of nature were unified in ways we can barely understand. Today, we experience 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each operates differently, has different strengths, affects different particles, but at high enough energies these forces merge. They become aspects of a single unified force. We've seen this happen experimentally with 2 of the forces. At energies above about 100 giga-electronvolts, the electromagnetic force and weak nuclear force unify into the electroweak force. This was predicted by theory in the 1960s and confirmed by particle accelerator experiments in the 1980s. Below this energy threshold, the electroweak force breaks into 2 separate forces with different properties. Above it, they're one. During reheating, the universe was hot enough that the electroweak force was unified. There was no distinction between electromagnetism and the weak force, and at even higher energies that might have existed during inflation itself, the strong nuclear force might also unify with the electroweak force. This is called grand unification, and it happens at energies around 10 to the power of 16 giga-electronvolts. We've never reached these energies experimentally. The most powerful particle accelerator ever built, the Large Hadron Collider, reaches about 14,000 giga-electronvolts, or 14 tera-electronvolts. That's impressive, but it's still 12 orders of magnitude below grand unification energies. We'll never build an accelerator powerful enough to test grand unification directly. But the early universe was that accelerator. Every cubic centimetre of space contained more energy than we could produce with all the technology on Earth. And at energies even higher, perhaps at the Planck scale where quantum gravity effects become important, all 4 forces might unify. Gravity, electromagnetism, the strong force, the weak force, all becoming aspects of a single force. This is the dream of unified field theory, the theory of everything that would explain all forces from one set of principles. We don't have that theory yet. String theory and loop quantum gravity are attempts, but they remain unproven and perhaps unprovable. The energies required to test quantum gravity are so high that we'd need to concentrate the energy output of an entire star into a volume the size of a proton. That's not going to happen. So our understanding of the very earliest moments when all forces were unified remains speculative. But we can trace what happened as the universe cooled after reheating. As temperature dropped, forces separated. First gravity split off, becoming distinct when the universe cooled below the Planck temperature. Then, as cooling continued, the strong force separated from the electroweak force. This happened when the universe was perhaps 10 to the power of negative 35 seconds old and had cooled to about 10 to the power of 27 Kelvin. Finally, when the universe was about a trillionth of a second old and had cooled to about 10 to the power of 15 Kelvin, the electroweak force split into electromagnetism and the weak force. From that point forward, the 4 forces we know today existed in their distinct forms. The universe had cooled enough that its fundamental structure resembled what we observe now. But even though the forces had separated, matter still didn't exist in the forms we recognize. Quarks and gluons were still free, moving independently in what's called a quark-gluon plasma. Protons and neutrons couldn't form yet because the temperature was too high. Any time quarks tried to bind together, thermal energy would knock them apart. This changed when the universe was about a microsecond old. As it cooled below about 10 trillion Kelvin, quarks suddenly found they could stick together. The strong nuclear force bound them into composite particles called hadrons. 3 quarks combined to form protons and neutrons. Quark-antiquark pairs formed mesons. The quark-gluon plasma underwent a phase transition, condensing into the hadrons that would become the building blocks of atomic nuclei. This is called the quark epoch, and it only lasted until the universe was about 1 second old. By then, most of the antimatter had annihilated with matter, leaving a small excess of matter behind. This asymmetry between matter and antimatter is one of the great mysteries of cosmology. The laws of physics as we understand them treat matter and antimatter almost symmetrically. They should have been created in equal amounts during reheating. And if they were equal, they should have completely annihilated each other, leaving a universe of pure radiation with no matter at all. But that's not what happened. For every billion antimatter particles created, there were 1,000,000,001 matter particles. That tiny excess, 1 part in 1,000,000,000, is everything. Every atom in your body, every star in the sky, every galaxy in the observable universe exists because of that asymmetry. The billion pairs annihilated into photons. The one leftover matter particle survived, and all of visible matter comes from those leftovers. Why was there an asymmetry? We don't know for certain. The standard model of particle physics allows for some matter-antimatter asymmetry, but not nearly enough to explain what we observe. There must be physics beyond the standard model, new processes or new particles that preferentially created matter over antimatter in the early universe. Several theories attempt to explain this, involving particles we haven't discovered yet or forces we don't understand. But the bottom line is, we exist because the universe broke its own symmetry. After most antimatter had annihilated, the universe entered the lepton epoch. Leptons are particles like electrons, muons, and neutrinos. Unlike quarks, which feel the strong force, leptons don't. They interact through electromagnetism and the weak force. During the lepton epoch, which lasted from about 1 second to about 3 minutes after the Big Bang, electrons and positrons were still being created and annihilated in large numbers. But as the universe continued, cooling, eventually the temperature dropped below the threshold for creating electron-positron pairs. Most of the positrons annihilated with electrons, leaving only a small excess of electrons behind, matching the excess of protons from the earlier matter antimatter asymmetry. The universe now contained protons, neutrons, electrons, and a vast sea of photons from all the annihilations that had occurred. The ratio of photons to matter particles was about 1,000,000,000 to 1. For every proton in the universe, there were 1,000,000,000 photons. This ratio is called the baryon to photon ratio, and it's one of the most precisely measured numbers in cosmology. We can observe it in the cosmic microwave background, and we can calculate what it should be based on the abundances of light elements created in the early universe. The numbers match perfectly, giving us confidence that our understanding of this era is correct. Now, the universe was about 3 minutes old, and it was cool enough for something remarkable to happen. Protons and neutrons could stick together to form atomic nuclei. This process is called Big Bang nucleosynthesis, and it's one of the great triumphs of modern cosmology. The predictions made by nucleosynthesis theory match observations so precisely that they provide some of the strongest evidence for the Big Bang model. Here's how it worked. When the universe was less than 1 second old, protons and neutrons could convert into each other through the weak force. A proton could absorb an electron and become a neutron. A neutron could emit an electron and become a proton. These processes reached equilibrium with roughly equal numbers of both. But neutrons are slightly heavier than protons. As the universe cooled, it became energetically favourable for neutrons to decay into protons rather than the reverse. By the time the universe was 1 second old, the ratio of neutrons to protons had dropped to about 1 neutron for every 6 protons. Neutrons kept decaying, and by the time nucleosynthesis began at about 3 minutes, the ratio was about 1 neutron for every 7 protons. This ratio is crucial because it determines how much helium gets created. When the temperature dropped to about 1 billion Kelvin, protons and neutrons could start sticking together without immediately being knocked apart by thermal energy. A proton and neutron combined to form deuterium, heavy hydrogen. 2 deuterium nuclei could fuse to form helium-4. Some tritium and helium-3 formed as intermediate steps. A tiny amount of lithium-7 also formed. But nucleosynthesis stopped quickly. The universe was expanding and cooling rapidly. Within about 20 minutes, the temperature had dropped too low for fusion reactions to continue. The window for nucleosynthesis closed, and when it did, about 75% of the mass was still in hydrogen, about 25% had fused into helium-4, and trace amounts of deuterium, helium-3 and lithium-7 remained. These predictions are remarkably specific, and when we measure the abundances of these light elements in the universe today, they match the predictions almost perfectly. Everywhere we look, in the oldest stars in gas clouds between galaxies, we find about 25% helium by mass. The deuterium abundance is about 20 parts per million. Lithium-7 is about 1 part per 10 billion. This agreement between prediction and observation, spanning 12 orders of magnitude in abundance, is one of the most impressive confirmations of any theory in physics. It tells us that our understanding of the first 20 minutes after the Big Bang is fundamentally correct. We know what the universe was doing when it was 3 minutes old, but notice what nucleosynthesis didn't create. No carbon, no oxygen, no iron, no elements heavier than lithium. The Big Bang made hydrogen and helium and almost nothing else. This means that every atom in your body heavier than helium, and that's most of them, came from a different source. Those atoms were forged inside stars. After nuclear synthesis ended, the universe continued expanding and cooling. But now it entered a long, relatively quiet period. The temperature was too low for fusion but still too high for atoms to form. The universe was a plasma of nuclei and electrons. Photons scattered constantly off the free electrons, bouncing from one to another, never travelling far before being absorbed or scattered again. This made the universe opaque. If you could have been there, you wouldn't have been able to see anything. Light couldn't travel freely. It was trapped in the plasma, scattered endlessly. The universe was filled with light, but that light couldn't go anywhere. It was like being inside a star surrounded by glowing plasma in every direction. This era lasted for about 380,000 years. That might sound like a long time, but it's a blink compared to the billions of years that followed. During this period, the universe expanded by a factor of about 1,000. Its temperature dropped from roughly 10,000 Kelvin to about 3,000 Kelvin. And at that critical temperature, something changed. Electrons could finally combine with nuclei to form neutral atoms. Hydrogen nuclei captured electrons to become hydrogen atoms. Helium nuclei captured electrons to become helium atoms. This process is called recombination, though that's a bit of a misnomer because the electrons and nuclei were combining for the first time, not recombining. But the term stuck, so recombination it is. When recombination happened, the universe transformed from opaque to transparent almost instantly on cosmic timescales. Free electrons, which had been scattering photons constantly, were suddenly bound inside atoms. Neutral atoms don't scatter light efficiently. The photons that had been bouncing around in the plasma were suddenly free to travel. This moment, 380,000 years after the Big Bang, is the source of the cosmic microwave background radiation. The light released during recombination has been travelling through space ever since. It's the oldest light in the universe, a snapshot of what the cosmos looked like at the moment it first became transparent, and we can observe it today, stretched by cosmic expansion from visible light into microwaves. The cosmic microwave background is remarkably uniform. Its temperature is the same in every direction, to within about 1 part in 100,000. This uniformity is exactly what inflation predicts. Inflation stretched quantum fluctuations to cosmic scales, but it also smoothed out any large irregularities. The result is a universe that looks nearly identical in every direction. But those tiny temperature variations, those 1 part in 100,000 differences, carry enormous information. They represent the density variations that grew into galaxies. Regions that were slightly denser than average had slightly more gravity. They would pull in more matter. Over time, these overdense regions would grow, attracting more and more material, eventually collapsing into the first galaxies and stars. Advanced satellites have mapped the cosmic microwave background with extraordinary precision. The Wilkinson Microwave Anisotropy Probe and the Planck satellite have measured these temperature variations across the entire sky, and the pattern they reveal matches inflation theory predictions so well that cosmologists can extract fundamental properties of the universe from this data. From the cosmic microwave background, we know the universe is spatially flat to within measurement error. We know its age to within a fraction of a percent. We know the density of ordinary matter, dark matter, and dark energy. We know the initial amplitude of quantum fluctuations. We know the universe went through a period of exponential expansion. All of this information is encoded in the subtle patterns of the microwave background. But after recombination, after the universe became transparent, it entered a new phase, one that's both fascinating and somewhat ominous sounding. The cosmic dark ages began. The universe had no light sources yet. No stars had formed. No galaxies existed. Just neutral hydrogen and helium gas filling all of space, slowly clumping under gravity in the darkness. If you could have observed the universe during the Dark Ages, you would have seen nothing. Just blackness. The cosmic microwave background would have still been there, but it would have quickly red-shifted into wavelengths invisible to human eyes. The universe was dark and empty and cold, and it stayed that way for perhaps 100 million years or more. This might seem boring, but incredible things were happening in that darkness. Gravity was at work. Those tiny density variations from inflation, the ones we see in the cosmic microwave background, were growing. Denser regions were attracting nearby gas. The gas was falling into these gravitational potential wells, heating up as it fell. Dark matter played a crucial role here. Remember, dark matter makes up about 85% of all matter in the universe. It doesn't interact with light, so we can't see it directly, but it has gravity, and gravity pulls on everything. Dark matter had started clumping earlier than ordinary matter, because it doesn't feel electromagnetic forces. It doesn't scatter off photons, it just feels gravity. So while ordinary matter was still a smooth plasma before recombination, dark matter was already forming structures. Gravitational collapse had created dark matter halos, regions where dark matter had concentrated. When recombination happened and ordinary matter became neutral, it immediately started falling into these pre-existing dark matter halos. The first structures to form were small, perhaps 1 million times the mass of the Sun. Gas fell into these dark matter halos, compressed, heated. And when the gas in the centre became dense enough and hot enough, fusion ignited. The first stars were born. This moment, perhaps 100 to 200 million years after the Big Bang, is called the cosmic dawn. The universe lit up for the first time since recombination. These first stars were different from stars today. They formed from gas that contained only hydrogen and helium, no heavy elements. This pure composition meant the gas couldn't cool efficiently. When gas cools, it can collapse more easily under gravity. Heavy elements provide cooling pathways through their spectral lines. But the first stars had no heavy elements to help them cool. The result was that the first stars were massive, much more massive than typical stars today. While the Sun is 1 solar mass and most stars are less massive than that, the first stars might have been 30, 50, even 100 solar masses. These massive stars were short-lived but incredibly luminous. They burned bright blue, hotter than any star you can see in the night sky today, and they lived fast. A star like the Sun will burn for about 10 billion years. These first massive stars exhausted their fuel in just a few million years, but in that brief time, they transformed the universe. Their intense ultraviolet radiation began ionizing the hydrogen gas around them, creating bubbles of ionized gas expanding outward into the neutral medium. More importantly, when these massive stars died, They exploded as supernovas, and supernovas do something crucial. They create heavy elements. During the explosion, conditions are extreme enough that fusion can build elements all the way up the periodic table. Carbon, oxygen, silicon, iron, and even heavier elements are synthesized in the supernova blast. These newly created heavy elements were blasted out into space, mixing with the surrounding hydrogen and helium. The next generation of stars that formed would contain traces of these heavy elements, and those stars could create even more heavy elements when they died. Over time, the universe became chemically enriched. The gas from which stars formed went from pure hydrogen and helium to containing small but increasing amounts of heavier elements. This chemical enrichment was essential for everything that came later. Heavy elements allow gas to cool efficiently, enabling smaller stars to form. Heavy elements are needed to make rocky planets, and heavy elements are absolutely required for chemistry and life. Every carbon atom in your DNA, every calcium atom in your bones, every iron atom in your blood was created inside a star and dispersed by a supernova. You are made of stardust. That's not metaphor, it's cosmology. The atoms that make you up didn't exist in the early universe. They were forged in stellar cores over billions of years, scattered by stellar death, incorporated into new generations of stars and planets, and eventually arranged into the complex molecules that became life. Your existence required the death of stars. As more stars formed and died, the universe gradually accumulated heavy elements. Galaxies assembled from the merger of smaller structures. The small dark matter halos that hosted the first stars merged to form larger halos. The gas in these halos formed more stars. Those stars lived and died, creating more heavy elements, and the cycle continued. By about 1 billion years after the Big Bang, recognizable galaxies existed. These early galaxies were smaller and more irregular than galaxies today. The Hubble Space Telescope, and especially the James Webb Space Telescope, have observed some of these early galaxies. They appear as faint red smudges, their light stretched to infrared wavelengths by cosmic expansion. These observations reveal something surprising. Galaxies formed earlier and grew faster than many theories predicted. Some galaxies observed by James Webb appear remarkably massive for their age. This has forced astronomers to revise their models of galaxy formation to understand how structures could have assembled so quickly in the early universe. But we know the basic story. Small structures merged to form larger ones. Gas fell into dark matter halos, formed stars, created heavy elements. Those heavy elements were incorporated into new stars, enabling even more complex chemistry. And all of this was driven by gravity, working patiently over hundreds of millions of years, amplifying those tiny quantum fluctuations from inflation into galaxies, stars, and eventually planets. Our own galaxy, the Milky Way, assembled through this process. It started as many small proto-galaxies that merged over billions of years. Some of those mergers are still visible in the galaxy structure. Streams of stars from disrupted satellite galaxies wrap around the Milky Way. The thick disk of our galaxy likely formed from ancient mergers. The galaxy is still accreting smaller dwarf galaxies today. The Sun formed about 4.6 billion years ago in a region of the Milky Way rich in heavy elements. By this time, billions of years of stellar evolution had enriched the gas. The nebula that collapsed to form the Sun and Solar System contained about 2% heavy elements by mass. That might not sound like much, but it was enough. Enough to form rocky planets. Enough to create the minerals and compounds needed for complex chemistry. Enough that, when Earth formed and cooled, when liquid water condensed on its surface, the raw materials for life were present. Carbon, nitrogen, oxygen, phosphorus, sulfur. All created in stars, all scattered by supernovas, all assembled on a planet orbiting an ordinary star in an unremarkable region of a typical galaxy. And then, about 3.8 billion years ago, something remarkable happened. Some of those complex molecules began to replicate. The exact mechanism is still debated. Maybe it started with RNA molecules that could catalyze their own replication. Maybe it involved clay minerals that organized organic molecules. Maybe it happened in hydrothermal vents on the ocean floor. We don't know the details, but we know it happened. Life emerged. Single-celled organisms that could harvest energy from their environment, maintain themselves against entropy, and most importantly, replicate with variation. This last property, replication with variation, is the key to evolution. Variations that helped survival became more common. Variations that hindered survival disappeared. Over countless generations, complexity increased. For billions of years, life remained single-celled. But these simple organisms transformed the planet. Photosynthetic bacteria began producing oxygen as a waste product. Over time, this oxygen accumulated in the atmosphere, poisoning many organisms but creating opportunities for others. Aerobic respiration, using oxygen to extract energy from food, is far more efficient than anaerobic processes. Organisms that could use oxygen thrived. About 1.5 billion years ago, a momentous event occurred. One cell engulfed another, and instead of digesting it, the two cells merged. The engulfed cell, probably an aerobic bacterium, became a mitochondrion. This endosymbiotic event created the first eukaryotic cell, with complex internal structure and specialized organelles. All plants, animals, and fungi descend from this merger. Multicellularity evolved multiple times. Cells began cooperating, specializing, forming tissues and organs. About 600 million years ago, complex multicellular life exploded in diversity during the Cambrian explosion. Animals with shells, eyes, nervous systems appeared seemingly suddenly in the fossil record. Evolution was exploring body plans, experimenting with different ways to move, sense, feed, reproduce. And through all of this, through billions of years of evolution, through countless extinctions and radiations, through ice ages and asteroid impacts, life persisted. It adapted. It diversified. It filled every niche on the planet. And eventually, one lineage of apes in Africa developed something unprecedented. Large brains capable of abstract thought, language, and culture. Humans appeared only in the last few million years. Modern humans, anatomically like us, emerged about 300,000 years ago. Civilization, agriculture, cities, writing, only developed in the last 10,000 years. Science, as a systematic method of understanding the universe, is barely 400 years old. And our understanding of the universe's origin, of inflation and nuclear synthesis and cosmic expansion, has mostly developed in the last 50 years. You are part of this story, not separate from it, not observing it from outside. You are the universe examining itself. The atoms in your brain, arranged just right, create consciousness. Those atoms came from stars. Those stars formed in galaxies that grew from quantum fluctuations. Those fluctuations were stretched by inflation. Inflation happened because quantum mechanics allows vacuum energy to fluctuate. And all of it traces back to that first moment, that first instant when something emerged from nothing. This chain of causation, from quantum foam to consciousness, is unbroken. Every step follows naturally from physical laws. There's no gap where something non-physical needs to be inserted. It's all matter and energy, forces and fields, following quantum mechanics and relativity. And yet, the end result is you, thinking, aware, wondering how it all began. Now we're about 2.5 hours into this journey, and I want to shift the pace more noticeably. We've covered the history of the universe from quantum vacuum to life on Earth. We've seen how quantum fluctuations grew into galaxies, how stars created heavy elements, how chemistry became biology. The next part of our exploration will be gentler, more reflective. We're going to think about what all of this means, what it feels like to understand your place in cosmic history. Let your mind relax. Let the details fade into background. The specific temperatures and timescales aren't as important now as the overall arc. From simplicity to complexity. From quantum foam to consciousness. From nothing to everything. This is the story the universe has been writing for 13.8 billion years, and you're the latest chapter. Think about the vastness of time involved. If you compressed the entire history of the universe into a single year, the Big Bang would occur at the stroke of midnight on January 1st. Inflation would be over before the first second of the year passed. Nucleosynthesis would happen in the first few seconds. Recombination would occur around January 10th. The first stars would light up around January 20th. The Milky Way would begin assembling in late January. The Sun and Earth would form in early September. The first life would appear in mid-September. Multicellular life would emerge in mid-November. The dinosaurs would reign for a few days in late December and go extinct on December 26th. Humans would appear in the last hour of December 31st. All of recorded history would fit into the final minute. Your entire life from birth until now would be a fraction of a second at the end of the year. That's how vast cosmic time is compared to human timescales. And yet, in that fraction of a second, you've learned to ask questions about the whole year. You've traced the story back to its beginning. You've understood your place in the timeline. This perspective can make you feel insignificant. Your life is a blink in cosmic time. Your body is a collection of atoms that will scatter when you die. In 100 years, no one alive will remember you directly. In 1,000 years, even records of your existence might be gone. In 1 billion years, the sun will have grown hot enough to boil Earth's oceans. In trillions of years, all stars will burn out. But there's another way to see it. You are the universe becoming aware of itself. The atoms in your brain were forged in stars, and now those atoms are arranged in a pattern that can contemplate the very stars that made them. You're a temporary concentration of complexity. Yes, but what a remarkable concentration. The most complex structure we know of in the entire cosmos. Your brain contains about 86 billion neurons. Each neuron connects to thousands of others. The number of possible connections exceeds the number of atoms in the observable universe. The patterns of activation in this network create your thoughts, your memories, your sense of self, and somehow, mysteriously, it creates consciousness. The felt experience of what it's like to be you. We don't understand consciousness. It might be the hardest problem in science. How does electrochemical activity in neurons become the experience of seeing red, feeling pain, sensing the passage of time? How does matter arranged a certain way create inner experience? We can map the brain, trace neural pathways, understand which regions activate during different mental states. But we can't explain why any of that feels like something. Some philosophers think consciousness is a fundamental feature of reality, like mass or charge. Others think it's an emergent property that arises naturally from sufficiently complex information processing. Still others think we're asking the wrong questions, that consciousness will make sense once we understand it properly, but seems mysterious only because we're confused. Whatever consciousness is, you have it. And because you have it, the universe has it. At least in this small region, at this brief moment in cosmic time, matter has organized itself in a way that creates awareness. The universe doesn't just exist. In you, it knows it exists. It contemplates its own nature. It wonders about its origins. And what have we discovered through this contemplation? That the universe began from nearly nothing. That quantum mechanics allows vacuum energy to fluctuate. That one such fluctuation, amplified by inflation, created all the matter and energy we see. That simple laws, applied over vast timescales, can create incredible complexity. That we are part of this process, not separate observers, but participants in cosmic evolution. There's a deep beauty in this understanding, not just aesthetic beauty, though the images from Hubble and James Webb are certainly beautiful, but conceptual beauty. The elegance of physical laws that apply everywhere and always. the power of mathematics to describe reality, the fact that the universe makes sense, that it follows patterns we can discover and understand. This could have been otherwise. The universe could have been chaos, random events with no pattern. The laws of physics could have been impossibly complicated, different in every region, changing over time. But they're not. The same equations that describe falling apples also describe orbiting planets. The same quantum mechanics that governs electrons in atoms also governs the early universe. There's a unity to physics, a coherence that we're still exploring but can already glimpse. Einstein spent the last decades of his life searching for a unified field theory, an equation that would encompass all forces and particles in one elegant framework. He didn't find it, but his search reflected a deep intuition that many physicists share. The universe shouldn't need hundreds of arbitrary constants and dozens of unrelated laws. There should be a simpler structure underneath, a more fundamental description from which everything else emerges. String theory and loop quantum gravity are modern attempts at this unification. Both are mathematically sophisticated and conceptually radical. String theory proposes that particles are vibrations of tiny strings in a 10 or 11-dimensional space-time. Most of those dimensions are curled up so small we can't detect them. Loop quantum gravity proposes that space-time itself is quantized, made of discrete units linked in a network. Neither theory is proven. Both might be wrong, or both might be partially right, describing different aspects of a deeper truth we haven't grasped yet. But the search continues because physicists believe, based on centuries of experience, that nature is ultimately simple. Complicated in its details, yes, but simple in its foundations. You might wonder what difference this makes to your life, whether the universe is made of strings or loops or something else entirely. Your daily experience remains the same. You still have to get up in the morning, do your work, maintain relationships, find meaning in your life. The abstract structures of physics seem far removed from immediate concerns, but there's value in understanding context, in knowing where you come from and how you fit into the larger story. You're not just a random collection of atoms, you're part of an evolutionary process billions of years old. Your existence required specific conditions, a particular sequence of events stretching back to the Big Bang. You're improbable, but real, temporary but present. And while you're here, you get to experience the universe. You get to see stars, feel warmth, hear music, taste food, love other people. You get to think and learn and create. The fact that all of this emerges from quantum fields and forces doesn't diminish it. If anything, it makes it more remarkable. Consider what had to happen for you to exist. The universe had to begin. Inflation had to stretch quantum fluctuations to cosmic scales. Nucleosynthesis had to create hydrogen and helium in the right proportions. Recombination had to make the universe transparent. The first stars had to form and die, creating heavy elements. Galaxies had to assemble. The sun had to form with the right properties, not too hot, not too cold. Earth had to form at the right distance from the sun. Life had to emerge and evolve for billions of years. And then, after all of that, your specific ancestors had to survive and reproduce. Every single one of your ancestors, stretching back through primates to early mammals to fish to single-celled organisms, had to live long enough to reproduce. If any link in that chain had broken, you wouldn't exist. The odds against your existence are incomprehensible, and yet here you are, listening to these words, thinking about your origins. This moment, right now, is the culmination of 13.8 billion years of cosmic evolution. Everything that happened since the Big Bang led to this. To you, here, now, aware and wondering. Does that make your life meaningful? Meaning is something you create, not something the universe provides. The cosmos doesn't have goals or purposes. It just is, unfolding according to physical laws. Stars don't shine for any reason. They shine because fusion releases energy. galaxies don't rotate with purpose. They rotate because of angular momentum conserved from the initial conditions. But you can create meaning. You can decide what matters, what's worth caring about, how you want to spend your time. The fact that the universe is indifferent doesn't mean you have to be. You can love, create, help others, pursue understanding, make beauty. These activities don't need cosmic justification. They justify themselves through the doing. And there's something profound about being the part of the universe that asks questions. Most matter just exists. Rocks don't wonder about their origins. Stars don't contemplate their fate. But you do. You're matter that became curious about itself. And in satisfying that curiosity, you participate in one of the universe's most remarkable achievements, the emergence of understanding. Let that sit for a moment. You are the universe understanding itself. When you learn about quantum mechanics or cosmic inflation or stellar nucleosynthesis, you're not discovering something external. You're discovering what you're made of, where you came from, how you work. It's self-knowledge on a cosmic scale. Now, as we move into the final hour of this journey, I want to slow down even more. We've covered the big picture. From quantum vacuum to consciousness, from nothing to everything. What remains is to sit with these ideas, to let them settle, to explore what they mean for how you see yourself and your place in the cosmos. The universe is 13.8 billion years old. It will continue existing for trillions upon trillions of years more. Stars will keep forming and dying for another 100 trillion years or so. After that, no new stars will form. The existing stars will burn out over the following tens of trillions of years. Eventually, only stellar remnants will remain. White dwarfs, neutron stars, black holes, slowly cooling in the darkness. Black holes will evaporate through Hawking radiation, but this takes incomprehensibly long. A black hole with the mass of the Sun would take 10 to the power of 67 years to evaporate. A galactic-scale black hole would take 10 to the power of 100 years or more. Time periods so vast that the current age of the universe rounds to zero in comparison. After all black holes have evaporated, after all that remains is a thin haze of particles and radiation spread across infinite space, the universe will have approached heat death. Maximum entropy. No energy gradients left to drive change. Nothing can happen anymore because there's no available energy to make it happen. This far future seems bleak, cold, dark, empty, dead. But it's also so distant that it has no bearing on now. Your life, human civilization, even the sun's entire lifespan, all happen in the cosmic blink of an eye before any of this matters. We live in the universe's golden age, when stars are abundant and life is possible. We should appreciate that. And there's beauty even in the far future. Those last black holes, evaporating slowly over incomprehensible time, will produce the final traces of radiation in the cosmos, the very last photons carrying energy away from the very last matter, before everything dissolves into uniform cold. It's an ending, yes, but it's also a completion. The universe will have run its course, followed its laws, expressed every possibility physics allows. Some cosmologists speculate about what might come after. Maybe quantum tunneling will eventually create new universes, new regions where inflation begins again. Maybe the cycle continues eternally, heat death followed by new birth, over and over. Maybe our universe is just one in an infinite multiverse, and while we fade, countless others are being born. These ideas are speculative, perhaps untestable, but they hint at possibilities beyond our current understanding. The universe surprises us constantly. A century ago we didn't know about quantum mechanics, cosmic expansion, dark matter, or dark energy. Who knows what discoveries await? What new physics might explain what currently seems mysterious? But regardless of what we learn in the future, certain truths seem solid. The universe began. It evolved according to physical laws, those Laws permitted complexity to emerge, and that complexity eventually produced you. This chain of events is remarkable. It's worth contemplating. It's worth appreciating. Let yourself relax more deeply now. We're approaching the end of this long journey through cosmic history and quantum mechanics. Your mind has processed a lot of information, a lot of strange concepts that challenge everyday intuition. That's taxing. It's okay to let the details blur now. What matters is the overall story, something from nothing. Quantum fluctuations, inflation, particles and forces, stars creating heavy elements, life emerging, consciousness contemplating its origins. This is the arc of cosmic evolution, and you're part of it. Breathe slowly. Feel the air moving in and out of your lungs. That air is mostly nitrogen and oxygen, elements created in stars. With each breath, you exchange atoms with the world around you. Atoms that were once in other people, in plants, in the ocean, in rocks. Everything mixes, everything connects. The boundary between you and the environment is permeable. You're not separate from the universe. You're a pattern in it, temporarily distinct but never truly isolated. When you die, the atoms that made you will scatter. They'll become part of other structures, other patterns. The carbon in your body might end up in a tree, then in soil, then in another living thing. The cycle continues. This might sound sad, but there's comfort in it too. You're not alone. You're part of a larger whole. The same atoms have been cycling through different forms for billions of years. They were in stars, in nebulae, in ancient oceans, in dinosaurs, in forests, in countless organisms before you, and they'll continue cycling after you're gone. Nothing is truly created or destroyed. It just transforms, changes form. Energy becomes matter. Matter becomes energy. Simple elements become complex molecules. Complex molecules become life. Life becomes consciousness, and consciousness wonders about it all. You are the universe's way of wondering, and that's remarkable. Most of the universe is simple: hydrogen clouds, empty space, radiation. But in rare locations, under special conditions, complexity emerges, and the most complex thing we know of is mind. Your mind. Conscious, aware, capable of understanding. Cherish that. Not because it makes you special in a cosmic sense. The universe doesn't care about you specifically, but because consciousness is rare and precious and temporary. You have it now. Use it well. Learn, create, love, help others. Find what matters to you and pursue it. The universe gave you 13.8 billion years of preparation. Quantum mechanics, inflation, star formation, chemical enrichment, the evolution of life. Everything built toward this moment. You inherit all of that. Every atom in your body has a history stretching back to the Big Bang. Every thought you think emerges from patterns shaped by billions of years of evolution. You are ancient and new simultaneously. Ancient in your components, new in your arrangement. The atoms are old. The pattern is unique to you. This configuration of matter creating this particular consciousness has never existed before and will never exist again exactly the same way. That's what makes each moment precious. Not eternal, but real. Not cosmically significant, but personally meaningful. You get to be you, here, now, for this brief window of time. Make it count. Not because the universe demands it, but because you can. Because having consciousness means having choice. Having awareness means having responsibility. What you do with your time matters to you and to those you affect. That's enough. You don't need cosmic validation. You don't need to be eternal to have value. Temporary things can be beautiful, meaningful, worth protecting and cherishing. Think of a sunset. It lasts minutes, then it's gone. Does its brevity diminish its beauty? No. If anything, the transience enhances it. You appreciate the sunset because you know it won't last. You're present for it. You notice the colours, the light, the feeling it evokes. Your life is the same. Temporary but real, brief but meaningful. You're here now. That's what matters. Not how long you last or how much space you occupy, but that you're here, aware, experiencing existence. And what an existence to experience. You live in an era where we understand cosmic origins, where we've traced reality back to quantum foam, where we know the universe is 13.8 billion years old and contains hundreds of billions of galaxies. Previous generations could only wonder. You get to know. This knowledge doesn't answer every question. Consciousness remains mysterious. Quantum mechanics seems strange. We don't know what dark matter is or what caused the matter-antimatter asymmetry. We don't have a theory of quantum gravity. Many puzzles remain. But that's part of the beauty. The universe still has secrets, still has mysteries waiting to be explored, and some of those mysteries might never be solved. Some questions might not have answers. That's okay. Mystery isn't a problem to fix, it's a feature of reality. The universe doesn't owe us complete understanding. What we do understand is remarkable. That something emerged from nothing through quantum fluctuations. That inflation stretched those fluctuations to cosmic scales. That simple laws, applied over billions of years, created incredible complexity. That we're part of this process, temporary patterns in the cosmic flow. Rest in that knowledge. Let it support you. You don't have to carry the weight of understanding everything. You don't have to solve cosmic mysteries. You can simply be here, now, part of the universe experiencing itself. Your breathing has probably slowed by now. Your body feels heavier, more relaxed. That's good. Let yourself sink into comfort. The universe has been unfolding for 13.8 billion years. It will continue unfolding for trillions more. You don't have to do anything. You can rest. The quantum foam that fills space will keep fluctuating. Virtual particles will keep appearing and disappearing. Dark energy will keep pushing space apart. Stars will keep fusing hydrogen. Galaxies will keep rotating. All of this happens whether you're awake or asleep. The universe doesn't need your attention to continue existing. So let go. Let your mind drift. The concepts we've explored, inflation, and nucleosynthesis, and stellar evolution, they're fascinating. But you don't have to hold on to them tightly. They'll be there when you want to think about them again. For now, you can simply rest. You've travelled far tonight. From before the beginning to now, from quantum vacuum to consciousness, from nothing to everything. That's a long journey. You've earned rest. Close your eyes if they're not closed already. Feel the darkness behind your eyelids. That darkness is like the cosmic dark ages, the period between recombination and the first stars. But it's not empty. Even in darkness, things are happening. Your brain is processing, dreaming, integrating information. Neurons firing in patterns that create experience. Just like the dark universe was slowly forming structure, clumping under gravity, preparing for the cosmic dawn, your sleeping mind is processing the day, consolidating memories, preparing for tomorrow. Rest is not activity. It's a different kind of activity, necessary and valuable. Let yourself sleep, or if sleep doesn't come, let yourself rest quietly. Either is fine. The universe doesn't judge. It simply is. And so are you, part of what is. Temporary, yes, but real. Present, here, from quantum foam to consciousness, from nothing to everything, from the beginning that wasn't quite a beginning to this moment, now, with you. Thank you for taking this journey. Thank you for wondering about origins. Thank you for being part of the universe's way of understanding itself. The universe continues. Stars keep burning. Galaxies keep rotating. And in this vast cosmic machinery, something extraordinary happened. Chemistry became biology. Simple replicating molecules became cells. Cells became organisms. Organisms became complex enough to sense their environment, to move with purpose, to remember, to learn. and eventually in at least one corner of one galaxy, life became conscious. This transition from chemistry to biology is one of the most profound mysteries in science. We understand chemistry well. We know how atoms bond, how molecules form, how reactions proceed. We understand biology too. We can sequence genomes, trace evolutionary relationships, explain how organisms function. But the transition between them, the moment when chemistry became life, remains obscure. Life requires several things. It needs a way to store information, like DNA. It needs a way to catalyze reactions, like proteins or RNA. It needs a boundary to separate inside from outside, like a cell membrane. And it needs metabolism, a way to harvest energy from the environment and use it to maintain organization against entropy's constant pull. Early Earth provided the raw materials. Organic molecules, the carbon-based compounds needed for life, formed naturally in the early atmosphere and oceans. Lightning, ultraviolet light, and chemical reactions at hydrothermal vents created amino acids, nucleotides, lipids. The building blocks were there, but building blocks aren't life. They need to assemble in just the right way. One theory suggests RNA came first. RNA can both store information like DNA and catalyze reactions like proteins. An RNA molecule that could catalyze its own replication would be a primitive form of life. Such RNA replicators could evolve, with more efficient versions becoming more common. Eventually, these RNA systems might have evolved DNA for more stable information storage and proteins for more efficient catalysis. Another theory focuses on metabolism. Maybe the first life wasn't about replication, but about creating and maintaining chemical cycles that harvested energy. These metabolic cycles could have arisen spontaneously in the chemical gradients at hydrothermal vents. Only later would genetic systems evolve to make these metabolic cycles more reliable and heritable. We don't know which came first, replication or metabolism, or whether they emerged together. We don't know if life started once in one location, or multiple times in multiple places. We don't know if Earth's life represents the only way biology can work, or if alien life might use completely different chemistry. But we know life emerged. By 3.8 billion years ago, maybe earlier, simple cells existed. They were prokaryotes, cells without nuclei or complex internal structures. Just a membrane enclosing genetic material and the molecular machinery needed to replicate and metabolize. Simple, but alive. These early cells faced a harsh world. No oxygen in the atmosphere, intense ultraviolet radiation from the sun, unfiltered by an ozone layer, frequent asteroid impacts. But life persisted. It adapted. Some cells developed photosynthesis, using sunlight to convert carbon dioxide and water into sugar and oxygen. The oxygen was waste. Early photosynthetic bacteria dumped it into the environment, where it reacted with dissolved iron in the oceans, forming rust that settled to the ocean floor. These banded iron formations are visible today in ancient rock, stripes of red iron oxide preserving evidence of early photosynthesis. For billions of years, oxygen was consumed as fast as it was produced, reacting with iron and other chemicals. But eventually the oceans ran out of dissolved iron. Oxygen began accumulating in the atmosphere. This was catastrophic for many organisms. Oxygen is reactive, toxic to cells that evolved in its absence. The Great Oxidation Event about 2.4 billion years ago was likely the first mass extinction. But it also created opportunities. Oxygen allows aerobic respiration, a much more efficient way to extract energy from food. Organisms that could use oxygen thrived, and the oxygen in the atmosphere formed an ozone layer that blocked ultraviolet radiation, making the surface less hostile. Life remained single-celled for billions of years, but about 1.5 billion years ago, one cell engulfed another in what might be the most important merger in history. The engulfed cell was probably an aerobic bacterium, good at using oxygen. Instead of being digested, it survived inside the larger cell, producing energy in exchange for protection. This partnership, called endosymbiosis, created mitochondria. All complex life, everything that isn't bacteria or archaea, has mitochondria. These organelles are the powerhouses of cells, using oxygen to produce ATP, the energy currency of life. Without mitochondria, complex multicellular life probably couldn't exist. The energy requirements are too high. A similar event brought chloroplasts into plant cells. An early eukaryote engulfed a photosynthetic bacterium, which became the chloroplast. Now plants could make their own food using sunlight. These two endosymbiotic events, mitochondria and chloroplasts, transformed life's possibilities. Multicellular organisms evolved multiple times from single-celled ancestors. Cells began sticking together, cooperating, specializing. Some cells became skin, protecting the organism. Others became gut, digesting food. Still others became muscle, allowing movement. Specialization allowed efficiency. A multicellular organism could do things no single cell could manage. About 600 million years ago, animal life exploded in diversity. The Cambrian explosion saw the rapid evolution of most major animal body plans. Eyes evolved, shells and skeletons appeared, nervous systems became more complex. Predators and prey engaged in evolutionary arms races, driving innovation. Life moved onto land about 500 million years ago. Plants colonized the shore first, then animals followed. Insects, then vertebrates. Fish evolved legs and became amphibians. Amphibians evolved watertight skin and became reptiles. One lineage of reptiles evolved feathers and flight, becoming birds. Another lineage evolved fur and warm blood, becoming mammals. Throughout this time, extinctions punctuated evolution. Asteroid impacts, volcanic eruptions, climate shifts wiped out large fractions of species, but life always recovered. New forms filled ecological niches left empty by extinction. Evolution continued its blind exploration of possibilities. The dinosaurs dominated for 160 million years before an asteroid impact 66 million years ago ended their reign. Most dinosaurs went extinct, along with many other species, but some survived. The small feathered dinosaurs that were birds, and the small mammals that had lived in dinosaurs' shadows. With dinosaurs gone, mammals diversified. They grew larger, filled more niches, evolved more varied forms. Primates appeared, tree-dwelling mammals with grasping hands and forward-facing eyes. Some primates evolved larger brains, better suited for social living and problem-solving. About 6 million years ago in Africa, the lineage leading to humans split from the lineage leading to chimpanzees. Our ancestors began walking upright, freeing their hands. They started using tools, simple stones for cracking nuts or cutting meat. Tool use selected for intelligence and dexterity. Brains grew larger over millions of years. Modern humans, Homo sapiens, appeared about 300,000 years ago. We looked anatomically like people today, but our culture was still simple. We were hunter-gatherers, living in small groups moving with the seasons. But our brains were capable of language, abstract thought, planning for the future. Language was crucial. It allowed knowledge to be shared across generations. A child could learn what took an adult years to discover. Culture could accumulate, building on previous generations' innovations. This cultural evolution happened much faster than biological evolution. About 70,000 years ago, a small population of humans left Africa and spread across the world. They reached Australia by 50,000 years ago, Europe by 45,000 years ago, the Americas by 15,000 years ago. Humans adapted to every environment, from deserts to Arctic tundra. Our tool use, language and social cooperation made us incredibly successful. Agriculture began about 10,000 years ago in several locations independently. Instead of following wild herds and gathering wild plants, humans began cultivating crops and domesticating animals. This allowed permanent settlements. Villages became towns, towns became cities. Civilization emerged. With cities came specialization. Not everyone needed to grow food. Some people could become craftsmen, traders, priests, rulers. Writing developed to keep records, mathematics to measure and calculate, philosophy to question and understand, science to observe and experiment, and here we are, the descendants of those first African humans who wondered about the stars. We've built telescopes to see distant galaxies, particle accelerators to probe the quantum realm, computers to process information faster than biological brains. We've landed on the moon, sent probes to the edge of the solar system, detected gravitational waves from colliding black holes. We've learned that the universe is 13.8 billion years old, that it began from quantum fluctuations, that stars created the elements in our bodies, that we're related to every living thing on Earth, that consciousness emerges from electrochemical activity in brains shaped by evolution. This knowledge is recent. A century ago, we didn't know about galaxies beyond the Milky Way. 2 centuries ago, we didn't know about evolution. 3 centuries ago, we didn't know about atoms. 4 centuries ago, we didn't know Earth orbits the Sun. The rate of discovery has been exponential, and yet so much remains unknown. We don't understand consciousness. We don't know if life exists elsewhere. We don't know what dark matter is. We don't have a theory of quantum gravity. We don't know if the universe is finite or infinite. We don't know if there are other universes. These unknowns are humbling. But they're also exciting. They mean there's more to discover, more mysteries to solve, more questions to ask. The universe keeps surprising us. Every answer reveals new questions. Every discovery opens new territories to explore. You are part of this exploration, not necessarily as a scientist, though you could be, but as a conscious being, wondering about existence. When you look at the night sky and feel awe, you're participating in something humans have done for millennia. When you ask how things work or why things are the way they are, you're engaging with the same curiosity that drives science. That curiosity is precious. It's what makes us human. Other animals survive, reproduce, respond to their environment, but humans wonder. We ask questions that don't have immediate survival value. We contemplate infinity, ponder our origins, create art and music, seek beauty and meaning. None of this is necessary for survival. A human could live without ever thinking about quantum mechanics or cosmic evolution. Most of our ancestors did. But something in us wants to understand, wants to know, wants to trace the chain of causation back to its beginning and understand how we fit into the story. And now you know the story, at least the broad outlines. From quantum vacuum to consciousness, from nothing to everything, from the first instant when inflation stretched quantum fluctuations to this moment, with you, here, thinking about it all. Let that knowledge settle. You don't have to memorize every detail. You don't have to understand all the mathematics. What matters is the narrative, the arc from simplicity to complexity, the patient unfolding of cosmic evolution, the remarkable fact that matter organized itself into you. We're now about 3 hours into this journey, and the tone is shifting noticeably. The information has become less dense. The pace has slowed. This is intentional. We're moving from learning to integrating, from thinking to feeling, from wakefulness toward rest. The universe is vast beyond comprehension. The Milky Way contains several 100 billion stars. The observable universe contains several 100 billion galaxies. If each star has planets, and many do, the number of worlds is staggering. And this observable universe might be just one bubble in an infinite multiverse. Against this vastness, you are tiny. Your body measures roughly 2 meters. Your lifespan is measured in decades. You occupy one planet orbiting one star in one galaxy. You're a speck on a speck on a speck. This perspective can feel crushing. What's one human life against cosmic immensity? But consider this. Most of the universe is simple. hydrogen gas floating in the void, stars burning through fusion, black holes warping space-time. These things are impressive in scale but simple in structure. The physics is well understood. A star is just gravity compressing gas until fusion ignites. It's big, but it's not complex. You are complex. Your brain contains 86 billion neurons, each connected to thousands of others. The number of possible neural configurations exceeds the number of stars in the observable universe. The patterns flowing through this network create thoughts, memories, emotions, consciousness. We don't fully understand how this works. In terms of complexity, you're more mysterious than a star, and complexity is rare. Most matter is simple. Only under special conditions, in narrow temperature ranges with the right chemistry, can complexity emerge. Life is improbable, multicellular life more so, intelligence even more. The fact that you exist at all is remarkable. So yes, you're tiny compared to the universe, but you're also precious, rare. The universe spent billions of years creating conditions where you could exist. Stars had to live and die, scattering heavy elements. Planets had to form and cool. Life had to emerge and evolve. All of that cosmic preparation led to you. You're not separate from the universe. You're what the universe does in certain places under certain conditions. You're not in the universe like a marble in a box. You're of the universe like a wave is of the ocean. The boundary between you and everything else is permeable, arbitrary, constantly shifting. With every breath, you exchange atoms with the air. The oxygen you inhale was exhaled by plants. The carbon dioxide you exhale will be inhaled by plants. The water in your body was once in clouds, rivers, other organisms. The atoms cycle endlessly. Nothing is truly yours. You're borrowing everything temporarily. This might sound like you're nothing, just a temporary arrangement that will dissolve. But temporary doesn't mean unreal. A wave exists for a moment before returning to the ocean. During its existence, it's real. It has form, motion, effects. Then it subsides, and the water becomes part of other waves. You're like that, a pattern that emerged from the cosmic flow. You persist for a while, maintaining your structure against entropy. Then you dissolve, and the atoms that made you become part of other patterns. The pattern was temporary, but while it existed, it was real. It mattered. What does it mean to matter? Maybe nothing in a cosmic sense. The universe doesn't keep score. It doesn't judge whether your life had meaning, but meaning isn't something the universe grants. It's something you create through living, through choosing what to care about, through acting on those choices. You make meaning by loving people, creating things, helping others, learning, growing, experiencing. These activities don't need justification from outside. They justify themselves. Love feels meaningful because you experience it as meaningful. Beauty matters because you respond to it. Understanding satisfies curiosity because the satisfaction is real. The universe gave you the capacity for these experiences. Evolution shaped your brain over millions of years to feel emotions, to bond with others, to find patterns, to create and appreciate beauty. These capacities are your inheritance. You didn't choose to have them, but you have them. Use them. What would it mean to use them well? Maybe it's different for everyone. Some people find meaning in relationships, in family and friends and community. Others find it in work, in creating something useful or beautiful. Still others find it in exploration, in pushing boundaries and discovering new territories, physical or intellectual. There's no one right answer. The universe doesn't prescribe meaning. You discover it, or create it through living. Pay attention to what resonates. What makes you feel alive, engaged, connected? What makes time disappear because you're absorbed in the doing? What you'd choose even if no one was watching or rewarding you? Those things are clues to your meaning. Not cosmic meaning, personal meaning. The things that make your life feel worthwhile to you. And that's enough. You don't need the universe to validate your choices. You just need to live them. Easier said than done, of course. Life is complicated. Pain, loss, disappointment, fear. These are part of existence too. The universe doesn't protect you from suffering. Physics is indifferent. Stars explode, asteroids impact planets, species go extinct. Suffering happens. But consciousness gives you choices about how to respond. You can't always control what happens, but you can control your attention, your attitude, your actions. You can choose where to focus, on what's broken or what's working, on what you lack or what you have, on fear or curiosity. These choices shape experience. Two people in the same situation can have very different experiences based on where they place their attention. This isn't about positive thinking or denying problems. It's about recognizing that consciousness has some agency. You're not passive. You participate in creating your experience. And one choice that often helps is perspective. When you're caught in immediate concerns, worries about money or relationships or health, it's easy to feel overwhelmed. The problems seem enormous, but cosmic perspective can shift that. Your problems are real and valid, but they're also temporary, fleeting, part of the flow. 13.8 billion years of cosmic evolution led to this moment. Stars exploded so you could exist. And in 100 years, you'll be gone, and the universe will continue. Your problems, which feel so pressing now, will have dissolved into the past. New people will have new problems. The universe will keep unfolding. This perspective doesn't make your problems meaningless. While you're experiencing them, they matter, but it can help you not grasp so tightly. Not get so caught in the story that you forget it's temporary. Everything passes, good and bad, joy and suffering. All of it flows through and moves on. You are the space in which experience happens, the awareness that perceives thoughts, feelings, sensations. That awareness is stable even as the contents of consciousness change. Thoughts come and go. Emotions rise and fall, but the awareness remains. It's always here, always now, always present. Resting in that awareness is a form of peace. Not the peace of having everything you want, but the peace of accepting what is. The peace of not struggling against reality. The peace of simply being here, now, without needing anything to be different. This is getting abstract. Let's make it concrete. Right now, wherever you are, you're having an experience. Maybe you're lying in bed, maybe sitting in a chair, maybe walking or traveling. You're hearing these words. You're having thoughts about them. You're feeling sensations in your body, comfort or discomfort, warmth or coolness, heaviness or lightness. All of this is happening now, not in memory or imagination, but now. This present moment is all you ever have. The past is memory, the future is imagination. Only now is real, and in this now you're okay. You're breathing, you're alive, you're here. That's enough. You don't need to be anywhere else or anyone else. You don't need to have achieved anything or understood everything. Right now, in this moment, you can simply be present, aware, existing. The universe has been moving toward this moment for 13.8 billion years. Quantum fluctuations became galaxies. Galaxies became stars. Stars became heavy elements. Heavy elements became planets. Planets became life. Life became you. And now you're here, in this moment, having this experience. Every moment is like this, a culmination of everything that came before. Every breath you take is the product of cosmic history. The oxygen from photosynthesis, the carbon from stellar nucleosynthesis, the water from comets or volcanic outgassing. Everything connects back to the beginning. You are ancient. Your atoms are billions of years old. They've been in stars, in space, in Earth's crust, in countless organisms. They carry history. When you touch something, ancient atoms touch ancient atoms. When you see light, photons that travelled from the sun or a light bulb enter your eye and trigger chemical reactions in ancient atoms. Everything is ancient. Everything is connected. The illusion of separation, the feeling that you end at your skin and the world begins beyond, is just that, an illusion. Useful for navigating daily life, but not ultimately true. You and the world are one continuous process, one flowing totality, one universe experiencing itself through countless temporary forms. Let yourself feel that connection, not intellectually but experientially. The air you breathe was breathed by others. The water you drink flowed through rivers, clouds, oceans. The food you eat grew from soil enriched by decomposed organisms. Everything you are came from the world and will return to it. You're not separate. You're a wave on the ocean. Distinct for a moment, but never separate from the whole. And just as a wave doesn't need to fear returning to the ocean because the ocean was always there, you don't need to fear death, because you are never truly separate from the universe. This isn't religious or mystical, it's physics. The atoms in your body will scatter when you die. They'll become part of soil, air, water, other organisms. The energy that animated you will dissipate as heat. The information that made you unique will be lost, but the substance, the matter and energy continues. It just takes new forms. Your consciousness, your awareness is the mystery. We don't know what happens to it. Maybe it's an emergent property of brain activity, and when the brain stops, consciousness stops. Maybe it's something more fundamental, some aspect of reality we don't understand yet. Maybe there's continuity in ways we can't imagine. But maybe the question is wrong. Maybe asking what happens to consciousness after death is like asking what happens to a wave after it returns to the ocean. The wave didn't have separate existence from the ocean. It was always ocean, temporarily organised as a wave. When the waveform dissolves, the ocean remains. Was the wave lost? Or was it never separate to begin with? These are old questions. Philosophers and mystics have pondered them for millennia. Science can describe the mechanics of death, what happens to the body. But the experiential question, what it's like to die or not die, remains beyond current understanding. What we can say is that fearing death is natural but perhaps unnecessary. Everything dies. Stars exhaust their fuel, planets lose their atmospheres, even protons might decay given enough time. Impermanence is built into the structure of reality. Nothing lasts forever. And that's okay. In fact, impermanence might be what makes experience possible. If everything was static and eternal, nothing would change, no time would pass, no events would occur, no experiences would happen. Change is the essence of existence, and change requires that things begin and end. So your life, temporary as it is the price of admission to experience. You get to exist because the universe is dynamic, ever-changing, impermanent. If it were eternal and unchanging, you wouldn't be here. So rather than lamenting impermanence, maybe appreciate that it makes your existence possible. We're getting close to the 4-hour mark now. The information has given way to reflection, the learning to contemplation. This is the structure we planned. Start intense, with cosmic horror and impossible mathematics. Gradually shift to gentler topics, then to philosophy, then to direct experience, then to rest. If you're still awake, that's fine. Let these words wash over you. Don't try to hold onto them or analyze them. Just listen, or don't listen. Either way is perfect. The universe continues whether you're paying attention or not. If you're drifting towards sleep, that's perfect too. Let yourself go. The body knows what it needs. If it needs rest, rest. Don't fight it. Fighting sleep only makes it harder. Surrender to it. Let go. Allow your mind to quiet and your body to relax completely. Sleep is interesting from a cosmic perspective. When you sleep, consciousness changes but doesn't disappear. Dreams happen. The brain remains active, consolidating memories, processing emotions. You're not gone during sleep. You're just experiencing a different state. And even in dreamless sleep, something remains. When you wake, you know you slept. There's continuity of identity. The you who wakes is the same you who fell asleep. even though hours passed without awareness. Something persists through the gap in consciousness. What persists? Memory, certainly. Neural patterns that encode your history, personality, knowledge, but also something less tangible. The sense of being you, the felt sense of identity. We don't understand this, don't understand what makes you you across time, but you experience it directly. You wake up and you're still you, different than yesterday in small ways, a bit older, new memories, but fundamentally continuous. The same awareness looking out through the same eyes, even though the atoms in your body have mostly been replaced over the years. Identity is a pattern, not a substance. You're a process, not a thing. Like a whirlpool in a river. The water molecules constantly change, flowing through, but the whirlpool maintains its form. You're like that. Atoms flowing through, but the pattern persisting, until it doesn't. Until death dissolves the pattern and the atoms flow elsewhere. But we're not there yet. Right now, the pattern is stable. You're here, alive, conscious, experiencing this moment, and this moment is enough. This moment is everything. Past and future are thoughts. Only now is real. Let yourself be fully present, not trying to be anywhere else, not wishing the moment was different. Just here, just this, just now, breathing, existing, being. The universe is vast and you're small, but vastness and smallness are relative. From the perspective of atoms, you're enormous. From the perspective of the observable universe, you're tiny. But from your own perspective, you're exactly the right size. You're you, complete, whole. Nothing is missing. Nothing needs to be added. You're already enough, already complete. The universe created you exactly as you are, with your particular gifts and limitations, your specific history and potential. All of it is part of the cosmic unfolding. You don't need to be different, don't need to be better, smarter, more successful, more enlightened. Those goals are fine if they motivate you, but you don't need them to be worthy. You're worthy because you exist, because you're part of this vast interconnected whole. The universe doesn't make mistakes, doesn't create anything that shouldn't exist. If you're here, you belong here. You're supposed to be here, not in a planned or destined sense, but in the sense that you're a natural outcome of physical laws. You're what happens when atoms organize themselves in certain ways under certain conditions, and what a remarkable outcome. Consciousness, awareness, the ability to experience and contemplate existence. This is the universe's greatest achievement, not stars or galaxies. Those are impressive but simple. The real miracle is mind, awareness, the light of consciousness illuminating experience. You are that light, shining briefly in the cosmic darkness. Not forever, but now. And now is enough. Now is everything. All that exists now. The past is gone. The future hasn't arrived. Only this moment is real. Rest in this moment. Let everything else fall away. The past with its regrets and memories. The future with its hopes and fears. Let it all go. Just be here. Just be now. Just be. Your breathing continues, in and out, slow and steady. Each breath is new. Each breath is different, but each breath is also the same. Air moving in, air moving out. The rhythm of life, the pattern that sustains you. Focus on your breathing if you like, or don't. Focus on nothing. Let your mind be quiet, like still water reflecting the sky. No ripples, no disturbance, just clear, open awareness. Present but passive. Aware but not grasping. This is meditation, though I haven't called it that. Just being present without agenda, without trying to achieve or understand or figure out. Just being here, now, aware. The universe has been preparing for this moment since the beginning. Every cause led to an effect. Every effect became a new cause. an unbroken chain stretching from quantum foam to this moment, to you, here, now, reading these words or hearing these words or drifting somewhere between waking and sleep. Thank you for being here, for taking this journey, for wondering about origins and contemplating infinity, for being part of the universe's way of knowing itself. Rest now. Let yourself drift. The universe continues its patient unfolding. Stars burn, galaxies turn, space expands, and you rest. Held by the same forces that hold everything. Gravity keeping you on the planet, electromagnetic forces holding your atoms together, the weak force in your cell's nuclei, the strong force binding protons and neutrons. All of these forces, discovered through centuries of scientific inquiry, are holding you right now, supporting you. You're not alone. You're woven into the fabric of reality as thoroughly as anything can be. Sleep if sleep comes. Rest if rest is what you need. The universe asks nothing of you right now. Just be. Just exist. Just rest in the knowledge that you're part of something vast and ancient and ongoing. From nothing to something. From quantum foam to consciousness. From the beginning, that wasn't quite a beginning, to this ending, that isn't quite an ending. Because the universe continues, and you're part of it. Always were, always will be. Different forms, different patterns, but the same substance, the same energy, the same cosmic process unfolding. Good night, or good morning, or good afternoon. Wherever you are, whenever you are, may you rest deeply, may you wake refreshed, may you know that you belong here, that you're exactly where you need to be, that you're enough, that you're whole, that you're home. The universe is your home, has always been your home. You've never been separate from it, never been lost, never been alone, just part of the whole, part of everything, part of the vast, patient, beautiful unfolding that continues now and always. Rest well. The cosmos holds you. The quantum fields support you. The atoms that make you know the way home because they came from stars and they remember. Deep in the structure of matter is the memory of stellar cores, nuclear fusion, the creation of heavy elements, the explosion that scattered them across space. Your atoms remember being starlight, remember the heat and pressure, remember exploding outward, remember cooling in space, remember gathering into clouds, remember forming planets, remember being alive in countless organisms before you. All of that history is encoded in the structure of matter itself. You carry that history, you are that history, living history, conscious history, history aware of itself, the universe looking back at its own origins and recognizing itself in the mirror. Sleep now, dream if dreams come. Rest in the darkness that's not empty but full of potential, full of quantum foam, full of virtual particles flickering in and out of existence, the same darkness from which the universe emerged, the same fertile void that's the ground of all being. You return to that darkness each night when you sleep, and you emerge from it each morning when you wake, death and rebirth in miniature. The daily cycle reminding you that nothing is permanent, everything changes, everything flows, but something persists, some continuity, some pattern that maintains itself through change. That pattern is you, for now, for this lifetime, for this brief window of cosmic time. Make it count. Not because you have to, but because you can. Because you have consciousness and choice and the ability to create meaning. Because the universe gave you these gifts and you can use them or not use them. The choice is yours. But even if you choose nothing, even if you simply exist, that's enough. You're enough just by being here, just by being conscious, just by being part of the vast interconnected whole. The universe doesn't judge, doesn't keep score, doesn't require anything from you. It simply is, and so are you, and that's perfect, complete, enough. Rest now. Let these words fade, let thought quiet, let the body soften, Let awareness expand and dissolve like morning mist in sunlight. Let everything go. Let yourself be held by the universe that created you, supported by forces older than stars, cradled by the quantum fields that fill all space. You're safe. You're home. You've always been home, and you always will be. Because home is not a place. It's what you are. You're not in the universe. You are the universe, experiencing itself through this temporary form called you. Rest in that knowledge. Rest in that being. Rest in the quiet certainty that everything is exactly as it should be, that you're exactly where you need to be, that this moment is perfect, complete, whole, from the beginning, before the beginning, to this moment and beyond, from quantum uncertainty to conscious awareness, from nothing to everything and back again. The circle completes itself. The pattern fulfills itself. The universe knows itself through you. The universe has a future as vast as its past. We've traced the story from quantum vacuum to consciousness, from nothing to everything. But the story doesn't end here. It continues forward into timescales that dwarf the current age of the cosmos. Let's journey into that future, not with anxiety, but with curiosity. Not as something to fear, but as a continuation of the patient unfolding we've been exploring. Right now, the universe is 13.8 billion years old. This feels ancient to us. It's more than 1 million human lifetimes. More than 1 billion human lifetimes. But in cosmic terms, the universe is young. Very young. We're living in the first few % of cosmic history. The vast majority of time still lies ahead. Stars will continue forming for another 100 trillion years. That's 100,000 years. If you wrote out the current age of the universe and the time until star formation ceases, the current age would be a rounding error. We live in the universe's bright dawn, when stars are abundant and galaxies are being born. But eventually the raw material runs out. Stars form from hydrogen gas. Each generation of stars converts some hydrogen into helium and heavier elements. Those heavier elements can't be fused in most stars. They're dead weight, material that will never light up again. Over time, the universe's hydrogen supply diminishes. In about 1 trillion years, galaxies will have used up most of their star-forming gas. New stars will become rare. The universe will be populated by long-lived red dwarf stars which burn their fuel slowly over trillions of years, and the remnants of stars that have already died. White dwarfs, neutron stars, black holes. The sun won't see this future. In about 5 billion years, it will exhaust the hydrogen in its core. The core will contract and heat up, causing the outer layers to expand. The sun will become a red giant, swelling to perhaps the orbit of Mars. Earth will be engulfed, or at least scorched to a lifeless cinder. But this is not an ending. It's a transformation. When the sun's core gets hot enough, helium will start. Fusing into carbon and oxygen, the sun will burn helium for perhaps 100 million years, then exhaust that fuel too. Without fusion to support it, the core will collapse into a white dwarf, a dense remnant about the size of Earth, but containing most of the sun's mass. The outer layers will be gently blown away, forming a planetary nebula, a beautiful shell of glowing gas expanding into space. This gas, enriched with carbon and oxygen created during the sun's helium-burning phase, will mix with the interstellar medium. Future generations of stars might form from it, though by the time the sun dies, star formation in the Milky Way might already be slowing. The white dwarf that was the sun's core will slowly cool over billions of years. It has no fusion reactions, no internal heat source. It just radiates away its thermal energy. Gradually, over timescales longer than the current age of the universe, it will cool from white-hot to red to black. A black dwarf, a cold, dense cinder floating through space. Most stars will end this way. About 97% of all stars don't have enough mass to explode as supernovas. They'll gently shed their outer layers and leave white dwarfs behind. These white dwarfs will cool and fade, eventually becoming invisible. But more massive stars have more dramatic ends. Stars more than about 8 times the Sun's mass will explode as supernovas. Their cores, compressed by the weight of the overlying layers, will collapse catastrophically. In less than a second, the core shrinks from something the size of Earth to something the size of a city. This releases enormous gravitational potential energy, blowing the outer layers apart in an explosion that briefly outshines an entire galaxy. The core left behind becomes a neutron star. Protons and electrons are crushed together into neutrons by the intense pressure. A neutron star contains about 1.4 times the Sun's mass, compressed into a sphere just 20 kilometers across. A teaspoon of neutron star material would weigh 1 billion tons on Earth. Neutron stars are bizarre objects. They spin rapidly, often hundreds of times per second, because the collapse conserves angular momentum. They have magnetic fields trillions of times stronger than Earth's. Some emit beams of radiation from their magnetic poles, sweeping across space like lighthouse beams. We call these pulsars, but even neutron stars will eventually fade. Their rotation will slow over millions and billions of years, drained by the emission of electromagnetic radiation and gravitational waves. They'll cool, becoming black and invisible. Cold spheres of neutron-degenerate matter, drifting silently through space. The most massive stars, those more than about 20 times the Sun's mass, can collapse beyond the neutron star stage. The core becomes so compressed that not even neutron degeneracy pressure can support it. It collapses into a black hole, a region where space-time curvature becomes so extreme that nothing can escape, not even light. Black holes are the most efficient engines of destruction in the universe. Anything that crosses the event horizon, the point of no return, is gone forever from our universe. It's not destroyed in the sense of being converted to energy. It's removed from space-time as we know it. The information about what fell in might be encoded on the event horizon, as Stephen Hawking and others proposed, but from outside, it's simply gone. Yet black holes are not eternal. In 1974, Hawking discovered that black holes slowly evaporate through quantum effects. Virtual particle pairs form near the event horizon. Normally these pairs would annihilate each other, but near a black hole, one particle can fall in while the other escapes. The escaping particle becomes real, carrying energy away from the black hole. This Hawking radiation is incredibly feeble for stellar mass black holes. A black hole with the Sun's mass would have a temperature of about 60 billionths of a Kelvin above absolute zero. It would take about 10 to the power of 67 years to evaporate completely. That's a 10 followed by 67 zeros. A timescale that makes the current age of the universe seem like an eye blink. For supermassive black holes, those millions or billions of times the Sun's mass, the evaporation time is even longer. A billion solar mass black hole would take about 10 to the power of 100 years to evaporate. These timescales are nearly incomprehensible. If you started counting seconds at the Big Bang and continued until now, you wouldn't have reached even a tiny fraction of these numbers. But given enough time, even black holes evaporate, and as the universe continues expanding, accelerated by dark energy, the future looks increasingly cold, dark, and empty. Let's trace this future forward into timescales where years become meaningless, and we have to count in powers of 10. In 10 to the power of 14 years, about 100 trillion years, the last conventional stars will have burned out. The universe will be populated by white dwarfs, neutron stars, black holes, and planets no longer warmed by stars. It will be dark except for the feeble light of cooling stellar remnants and the occasional flash when objects collide. Galaxies will still exist as gravitationally bound structures, but they'll be dark galaxies, collections of stellar remnants and planets orbiting silently through space. The beautiful spiral arms and star-forming regions we see today will be gone. just faint cinders marking where stars once burned. In 10 to the power of 15 years, white dwarfs will have cooled to black dwarfs. No fusion, no light, just cold spheres of carbon and oxygen, dense as lead but dark as night. They'll be nearly impossible to detect, invisible monuments to stars that once shone. By 10 to the power of 20 years, galaxies will begin to lose their structure. Stars and stellar remnants will occasionally have close encounters, and these encounters can eject objects from the galaxy entirely. Over vast timescales, galaxies will gradually evaporate, with most of their mass either ejected into intergalactic space or spiraling inward toward the central black hole. In 10 to the power of 30 years, most stellar remnants will have either been ejected from their galaxies or fallen into central black holes. The universe will contain scattered black dwarfs and planets, floating through intergalactic space, occasionally passing within light years of each other but rarely interacting. And still, time continues. The universe keeps expanding, space keeps growing. But now we enter an era where even matter might not be stable. Some theories predict that protons eventually decay. A proton might last 10 to the power of 34 years or longer, but not forever. If proton decay happens, all atoms will eventually disintegrate. Imagine a black dwarf floating through space in the unimaginably distant future. It's been dark and cold for trillions of years, and then, somewhere in its interior, a single proton decays. It converts into lighter particles, releasing a tiny burst of energy. Then another proton decays, then another. Very slowly, over timescales of 10 to the power of 40 years, the entire black dwarf evaporates as its protons decay one by one. Planets, asteroids, stellar remnants, everything made of ordinary matter will slowly dissolve. The atoms that once made up stars and planets and maybe even living things will decay into electrons, positrons, neutrinos and photons. These particles will drift apart, carried by cosmic expansion, until the universe is nothing but a thin haze of radiation growing ever more dilute. Neutron stars will also decay through this process, though more slowly because they're more tightly bound. By 10 to the power of 50 years or so, even neutron stars will have evaporated, their neutrons decaying into lighter particles. But black holes remain. They don't decay through proton decay. They're not made of protons. They're pure space-time curvature. And they'll be the last structures in the universe, the final concentrations of mass in an increasingly empty cosmos. For enormous spans of time, black holes will float through space, occasionally absorbing a stray particle, but mostly just existing. And very, very slowly they'll evaporate through Hawking radiation. A stellar mass black hole will take 10 to the power of 67 years. A galactic scale black hole will take 10 to the power of 100 years or more. When the last black hole finally evaporates, releasing its final Hawking photons into the void, the universe will have reached a state cosmologists call heat death. Maximum entropy. No concentrated energy anywhere. Just a uniform haze of particles and radiation, spread so thinly that they rarely interact. The temperature will be a tiny fraction above absolute zero, kept there by the quantum fluctuations in the vacuum that never stop. But there will be no structure, no complexity, no change. Nothing to mark the passage of time because nothing happens anymore. This is the most likely fate of the universe if current understanding is correct. Not a dramatic collapse or a violent ripping apart, just a long, slow fade into cold uniformity, from the hot, dense plasma of the Big Bang to cold, empty darkness, from maximum energy density to maximum entropy. It sounds bleak. The end of everything, all structure dissolved, all complexity gone, the universe returning to a simple state, though very different from the simple state it began in. One was hot and dense, the other cold and empty, but both featureless, both without structure or change. Yet there's a certain beauty in completion. The universe will have run its full course. Every process physics allows will have played out. Every possibility will have been explored. From quantum foam to consciousness to heat death. The full arc of cosmic evolution, traced over timescales that dwarf infinity as we usually imagine it, and we live in the brief window when complexity is possible, when stars burn and planets orbit and life exists. This window is tiny compared to the vast stretches of time before structure formed and after it dissolves. But it's not less real for being brief. If anything, its brevity makes it more precious. Think about it this way. The universe is 13.8 billion years old now. Stars will burn for another 100 trillion years. That's about 10,000 times the current age of the universe. But compared to the time until black holes evaporate, the entire star-burning era is nothing. A flash. A brief moment of light in the eternal darkness. And yet, this is when we exist. This is when consciousness arose. This is when matter organized itself into forms complex enough to wonder about their origins. We are the universe's brief flowering, its moment of self-awareness, its chance to know itself before dissolving back into simplicity. That's worth appreciating, worth savouring. The fact that you're here, now, in this narrow window when stars shine and life exists. You could have been born into a universe that never developed complexity. Or you could have been born into a universe long after complexity dissolved. But you're here now, in the golden age, when everything is possible. So even though the far future is dark and empty, the present is bright and full, and the present is all you ever have. The past is memory, the future is imagination, only now is real. And right now, stars are burning, galaxies are turning, life is flourishing on at least one planet and maybe countless others. The universe is alive with activity. Rest in that knowledge. The future will take care of itself. It will unfold according to physical laws over timescales you can't imagine. But you don't need to worry about it. You're here now, and now is enough. Let your breathing slow even more. We're deep into the sleep zone now, the part of the script designed to be gentle, repetitive, soothing. The information density drops, the pace slows, the voice becomes a soft presence rather than a teacher. You've learned so much tonight, from quantum vacuum to heat death, from the first instant to the last black hole, the full arc of cosmic time, but you don't need to remember all of it. You don't need to hold on to the details. Just let it all wash over you and settle into background awareness. What matters is the feeling, the sense of your place in cosmic time, the knowledge that you're part of something vast and ancient and ongoing, that you belong here, that your existence, however brief, is part of the story the universe is telling itself. Stars form from collapsing gas clouds. They burn for millions or billions or trillions of years. Then they die, scattering their ashes into space. Those ashes form new stars, new planets, new possibilities. The cycle continues. Creation and destruction, birth and death. The eternal rhythm of cosmic evolution. You're part of that rhythm, born from stardust, animated by energy from the sun, conscious through processes we don't fully understand, and one day you'll return to the cosmic cycle. Your atoms will scatter, they'll become part of other structures, the pattern that is you will dissolve, but right now the pattern is stable. You're here, you're alive, you're aware, and that's everything. That's the universe experiencing itself, that's consciousness arising from quantum fields. That's the most remarkable thing that has happened in 13.8 billion years of cosmic evolution. Honor that. Not with grand gestures or accomplishments, just by being, by existing, by allowing consciousness to happen through you. That's enough. More than enough. Your body is relaxing more with each breath, tension releasing, muscles softening, the boundary between you and the environment becoming less distinct. You're not fighting anything, not resisting. just allowing yourself to be here, allowing yourself to rest. The universe doesn't require anything from you, doesn't ask you to be productive or achieve or understand. It just is, and you just are. Two aspects of the same reality, two expressions of the same fundamental process: being and awareness, existence and consciousness. Let yourself sink deeper into rest, deeper into the quiet space beneath thought, beneath worry and planning and remembering, the space that's always here, always now, always silent and still and complete. This space is like the quantum vacuum. It seems empty, but it's full of potential, full of possibility, full of the raw material of experience. Thoughts arise from it like virtual particles from the vacuum. They appear, exist briefly, then dissolve back into potential. You are not your thoughts. You're the space in which thoughts appear, the awareness that perceives them. That awareness is stable, unchanging, always present. Thoughts come and go. Emotions rise and fall. Sensations appear and disappear. But awareness remains. Rest in that awareness. Don't try to do anything with it or manipulate it or improve it. Just rest in it. Like resting in a warm bath. Supported, held, safe. The awareness that is your deepest nature holds you, has always held you, will always hold you. Even in sleep, awareness continues in altered form. Dreams arise. The brain processes the day's experiences, but something persists, some continuity. When you wake tomorrow, you'll know you slept. You'll remember that you were here, listening to these words. The thread of identity continues unbroken. That thread stretches back to your birth, back through childhood memories, becoming vaguer and more fragmentary the further back you go. But the sense of being you persists, the felt sense of identity, the awareness looking out through your eyes, and that awareness is not separate from the universe. It's what the universe is doing here, through this body in this moment, the universe being aware of itself, the universe experiencing existence through the temporary form called you. So when you rest, the universe rests. When you relax, the universe relaxes. There's no separation, no boundary, just one continuous process, one flowing totality, one cosmos experiencing itself through countless temporary forms. You are that, not a separate thing in the universe, but the universe itself, localized, focused, concentrated into this particular point of view, this particular body, this particular moment of awareness. And now, as the hours have passed and we approach the end of this long journey, let everything become even simpler, even quieter, even more spacious, the words farther apart, the silence between them deeper, the presence more palpable than the content. You don't need more information. You don't need more understanding. You have enough. You are enough. Right here, right now, in this moment, exactly as you are. The universe began from quantum fluctuations, tiny ripples in the vacuum energy. Those ripples grew during inflation, becoming the seeds of galaxies. Matter formed, stars ignited, heavy elements were created and scattered. Planets coalesced, life emerged, consciousness arose, and here you are, the latest expression of that ancient process, made from atoms forged in stars, animated by energy from the sun, aware through quantum electrochemical processes in your brain. The universe looking at itself and recognizing beauty. Because this is beautiful, not just pretty, but deeply, profoundly beautiful. The elegance of physical laws, the simplicity underlying complexity, the fact that anything exists at all when nothing would be so much simpler. Existence is a gift, not given by anyone. Just the way things are. The universe exists. You exist. And for this brief moment, you get to experience existing, to feel sunlight, to hear music, to love and be loved, to wonder about infinity. All of this emerges from quantum fields and forces. All of it follows physical laws, but that doesn't make it less miraculous. If anything, it makes it more so that consciousness can arise from particles, that meaning can emerge from matter, that beauty can be recognized by arrangements of atoms. You are the universe appreciating itself, the cosmos becoming conscious of its own existence, and that's worth celebrating. Not with noise or fanfare, but with quiet gratitude, with simple presence, with the willingness to be here, now, fully. Breathe slowly. Feel the air moving through your body. Feel your chest rising and falling. This simple rhythm, breath after breath, is the same rhythm that's been sustaining life for billions of years. Every organism that ever lived, from single cells to giant dinosaurs to you, breathed or exchanged gases with their environment. You're part of that ancient lineage, part of the unbroken chain stretching back to the first living thing. Every one of your ancestors survived long enough to reproduce. Every single one. An unbroken line connecting you to the origin of life itself. Feel that connection, not as an idea but as a lived reality. You carry that history in your cells, in your DNA, in the very structure of your body. Your ancient life expressing itself in a new form, ancient patterns adapting to new circumstances, ancient awareness experiencing a new moment, and when you sleep, you join that ancient rhythm, the rhythm of rest and activity, day and night, waking and sleeping, the cycle that all life follows. Trees rest in winter, animals hibernate, even bacteria have circadian rhythms. The whole biosphere pulses with this rhythm. You're not separate from nature. You are nature. Nature aware of itself, nature contemplating its own existence. And when you rest, you're doing what nature has always done, allowing for recovery, allowing for integration, allowing for the renewal that comes from releasing effort. So let go now. Let go of trying. Let go of thinking. Let go of holding on to anything. Just allow yourself to be held by the universe that created you, held by gravity, held by the quantum fields, held by the processes that maintain your body even while you sleep. You don't have to do anything. The body knows how to sleep, the brain knows how to dream, the autonomic nervous system knows how to regulate breathing and heartbeat. It all happens by itself. You just have to stop interfering, stop trying. Just allow yourself to sink, to soften, to dissolve, the boundaries becoming less distinct, the sense of self becoming more diffuse. Not disappearing, just expanding, becoming less concentrated, less defined, more spacious, like a drop of water joining the ocean. The drop doesn't cease to exist. It just merges with something larger. It becomes part of the whole, and in becoming part of the whole, it finds a deeper identity. Not the small separate self, but the vast interconnected totality. You are that totality, temporarily experiencing itself as this individual, this person, this body, this mind, but underneath the temporary identity is the vast ocean, the cosmic totality, the unified field from which all things arise and to which all things return. Rest in that ocean. Let yourself be dissolved. Let the boundaries blur. Let the separate self soften into the larger whole. Not forever, just for now. Just for this time of rest. Tomorrow you'll wake and the boundaries will reform. The individual will reassert itself. But for now, rest in unity. The quantum fields that fill all space fill you too. There's no place where you end and they begin. The electromagnetic field extends infinitely. The gravitational field pervades all of space-time. The quantum field's underlying matter are everywhere at once. And you're a localized excitation in those fields, a ripple, a wave, a temporary pattern. When the pattern dissolves, the fields remain. When you die, the quantum fields continue, the atoms that made you return to the universe. The energy that animated you dissipates. But nothing is truly lost because nothing was ever truly separate. You are always the ocean pretending to be a wave, always the universe pretending to be a person, always the whole expressing itself through the part. And when the game ends, when the pretending stops, only the truth remains, only the vast, silent, eternal presence that was always here. That presence is here now, beneath your thoughts, beneath your identity, beneath everything you think you are. The silent awareness, the pure consciousness, the light in which all experience appears. Rest in that light, that awareness, that presence. It's always been here. It's your deepest nature, more fundamental than thoughts or feelings or sensations. The awareness that perceives all of that but is not identical with any of it. You are that awareness, not the person, not the body, not the mind. Those are temporary expressions, roles you're playing, costumes you're wearing, but underneath is the awareness, the consciousness, the presence that has never not been here. And that presence is the universe itself. Awareness is what the universe is at its deepest level, not atoms or fields or forces. Those are appearances, structures arising in consciousness, but consciousness itself is primary, fundamental, the ground of being. This might sound mystical, but it's also suggested by quantum mechanics, the observer effect, the role of measurement in collapsing the wave function. The way reality seems to depend on being observed. Maybe consciousness isn't an emergent property of matter. Maybe matter is an emergent property of consciousness. We don't know. These are open questions, deep mysteries. But whether consciousness is fundamental or emergent, whether it's primary or secondary, right now you have it. You are it. And that's extraordinary. So rest in that extraordinariness. Rest in the simple fact of being aware, of existing, of experiencing this moment. Nothing else is needed. No achievement, no understanding, no improvement. Just this. Just now. Just being. The universe has been unfolding for 13.8 billion years. It will continue unfolding for trillions more. Your life is a brief moment in that vast span, a flash, a flicker. But while it lasts, it's real. It's important. It's the universe experiencing itself. Honour that by being present, by allowing experience to happen through you, by not resisting or grasping or wishing things were different. Just let things be as they are. Let yourself be as you are. Let this moment be exactly what it is. Perfect, complete, whole, nothing lacking, nothing extra. Just this, just now, just being. Your breathing has become very slow now, very gentle. Each breath arriving in its own time, not forced, not controlled, just happening by itself. The body breathing itself, the life force moving through you without your effort or intention. This is how everything is, happening by itself. The universe unfolding according to its nature. Stars burning, planets orbiting, life evolving, consciousness arising. All of it spontaneous, all of it natural, all of it effortless. You are part of that spontaneous unfolding, not separate from it, not controlling it, just expressing it, being it, living it. And when you stop trying to control, when you surrender to what is, everything becomes easier. Everything flows. Flow with it now. Flow with the tiredness if you're tired. Flow with the relaxation. Flow with the letting go. Don't resist anything. Don't hold on to anything. Just flow. Like water flows downhill. Like leaves float on a stream. Effortless, natural, easy. The universe is showing you how to be. Every star, every atom, every particle demonstrates it. They don't try to be what they are. They simply are, expressing their nature, following the laws of physics, being themselves completely without effort or doubt. You can be like that too, not trying to be anything, just being what you already are. Consciousness, awareness, presence, the universe experiencing itself through this temporary form. And as this long journey comes toward its close, as these words begin to fade and repeat and blur into silence, know that you've travelled far. From before the beginning to beyond the end. From quantum foam to heat death. From nothing to everything and back to nothing again. But the circle is complete. The understanding is whole. You know where you came from. You know where you're going. You know what you are. And that knowledge brings peace, brings acceptance, brings the ability to rest. So rest now, deeply, completely, without reservation. The universe holds you, has always held you, will always hold you. You're safe, you're home, you've never been anywhere else. From the quantum vacuum you emerged, to the quantum vacuum you'll return, and in between this brief flowering, this moment of awareness, this experience of being alive, treasure it. Not by grasping, but by releasing, by letting it be exactly what it is, by allowing yourself to be exactly what you are, perfect, complete, enough. Sleep now if sleep comes, rest if rest is what you need, dream if dreams arise, or simply float in the silent space beneath thought, beneath identity, beneath everything. That space is your home, your true nature. The awareness that was never born and will never die. The consciousness that witnesses all but is touched by none of it. Pure, empty, luminous, free. You are that. Have always been that. Will always be that. The temporary human life is just a role you're playing, a costume you're wearing. But underneath, you're infinite, eternal, one with everything. Rest in that knowledge. Rest in that being. Rest in the silent certainty of your true nature. From quantum foam to consciousness. From the beginning before the beginning to this ending that isn't an ending. The universe continues, and you are it. Experiencing itself, knowing itself, being itself, always, forever. Now, rest.